We'll wait for another couple of minutes for people to join. But if someone could already confirm that they can hear me online, that would be nice.
We can hear you.
Excellent, thank you. Okay, let's get started. I'll share my screen. Okay, and let me switch to the presentation. Okay, switch this around. Okay, I'm ready to go. So, welcome to this training. It's a training organized by the Flemish Supercomputing Center, and it's in collaboration with UCC Belgium. So this is an international training. This is a link and a QR code that brings you to a repository that contains all the material for this training. It would bring you here. I'll put a link in the chat as well because that's more convenient for online participants. There you go. So this website, a very small website, just contains some information about this training, the table of contents, etc., etc. More importantly, it links to a GitHub repository, which is this one, and that contains, on the one hand, the slides for this training, and on the other hand, also a directory with source code. So basically, all the examples which are in the slide, all the notebooks I will show you interactively, are all in this directory. So they are available to you. You can clone or fork this repository as you see fit. It's not a problem. It's licensed, so as long as you abide to the license, everything goes. Okay. Another thing you might want to do is to stay connected with us via LinkedIn. So this is the LinkedIn feed for the Flemish Supercomputing Center, and you will find information there about trainings, about other events, and also things interesting for those into supercomputing and high performance computing. Okay, some practical things. So for the slides, I use monospaced font in order to make source code, fragments, and names stand out a little bit in running text. It makes it a little bit easier to interpret the slides. So for longer fragments, same font, but on a grayish background, just to make it stand out a little bit. When there is a data file rather than a file with code, it's similar font, but on whatever this is, greenish, yellowish background to make it a little bit visually distinct. from a source code file. What you see from time to time is these ellipses. So basically that means that something was left out, either because it was explained on the previous slide, or because it will be explained on the next slide, or it's fairly trivial, like in the case of this data file, that just means more of the same. And of course, the reason for that is screen real estate. Yeah, you'd have to try and fit lots of code onto a slide, and that's not particularly convenient. Most of the time, though, I will use notebooks rather than slides in order to do the presentation. Okay, so other practical things. So basically, the more interactive this is, the more pleasant it is for me, and perhaps also for you, and it might certainly be more useful for you if you ask questions. So feel free to do that via the chat. If it's too long to type in or too tedious to type in, I will ask you to activate your microphone so that you can ask your question verbally. Okay, another practical thing is that this session is recorded. Due to GDPR restrictions, of course, I don't make this recording publicly available. However, participants can send me an email afterwards and they'll get a link to the recording. Note that processing the recording takes a while. So basically, first Blackboard, which is the platform we are using, will have to process the video. That takes up to 2 hours. Then I need to download it and upload it again to YouTube, which will also process the thing, which takes quite some time. So basically by this evening or tomorrow morning, normally everything should be fine and you can ask for the link. Feel free to do so. It's available. It will be available to you. Okay, that was the practical stuff. Let's get into some motivation and perhaps why Python and data science are an interesting combination. I would argue, of course, otherwise I wouldn't be giving this training, that Python is quite well suited for data science. Why? Because it is a very terse language, which basically means that with little source code, you can express quite a lot of non-trivial logic. Also, it's an interpreted language, which basically means you write code you run. You don't have to compile, etc. So basically, that's nice. It's very useful for prototyping, again, because of these two first characteristics, and it allows for fast development. And that is, of course, in data science, often quite useful. And then, of course, there is Jupyter Notebooks, which make it very easy to interactively explore data, to do what I would call code exploration, programming exploration, and that is something that is facilitated quite a bit by Jupyter Notebooks. I will come back to Jupyter Notebooks later, because you can discuss whether it is suitable for reproducible science. Yeah, that is something to consider, but that's for later. It's also easy to access information with Python because there is a huge ecosystem of packages that allow you to access different kinds of information, like for instance text-based information. One of the formats which is very often used, of course, is CSV or JSON or YAML, and of course Python has libraries in order to deal with that, many even just in the standard Python library. Then of course there are regular expressions which make it very convenient and easy to manipulate textual data, to extract from it, to transform it, and so on. Then of course there is also a lot of web-based information. Information is published, you want to actually use that in order to do some processing. And again, the standard library helps you out, but personally I prefer Beautiful Soup, which is a Python package specifically designed for web scraping in convenient and easy ways. Then of course a lot of information is stored in relational database systems, and their SQL Alchemy and some other packages can come to the rescue and bridge your program and those data sources in a convenient and structured way. So basically, the rich ecosystem really helps to position Python as a language which is very suited for data science. And then, of course, you need to represent data, and for that, libraries such as Pandas, which give you data frames, or Polars, it's let's say younger sibling in a way, are very convenient as well. And then, of course, a very important part of data science is visualization. And for that, there are quite a number of very suitable libraries, such as, for instance, Seaborn and HoloViews. And we can talk about those in a bit more detail later on. And then, of course, it's also, I would argue, still the go-to language for machine learning, with deep learning frameworks such as Keras, TensorFlow, PyTorch, and so on, but also the very nice and venerable scikit-learn, which is very useful as well. On the one hand, for setting up pipelines, and on the other hand, for, let's say, the classic machine learning, which is not the deep learning frameworks which are mentioned here. So that as well is quite useful. Okay, so the first thing perhaps to deal with is Pandas, and essentially and nowadays you have a choice, in the sense that you can either go for Pandas or you can go for Polars, and both have their merits. So I'll discuss that a little bit first. So Pandas has been along for quite a while, been around for quite a while, and basically it is very ubiquitous. So the major advantage of it, in my opinion, is that to find information about Pandas, to find good tutorials, to get help from generative AI systems such as ChatGPT or Codex, it's much more easy to get that using Pandas. So that is definitely an advantage. A bit of a drawback is that Pandas shows its age, in the sense that indeed it's a bit slower than Polars. Question is, does that matter? Of course, it depends a little bit on what you are doing. So basically, if you are exploring data, then unless you work on really, really huge data sets, speed is not an important thing. Then convenience and, let's say, a rapid development cycle, so easily getting information, is in fact much more important than raw processing speed. So in that respect, I would say that Pandas in that sense still has the edge, although it is indeed a bit slower than Polars. So we can make a comparison later on. Is it easy to rewrite Polars into Pandas and vice versa? It's a slightly different way of thinking. I'll show you both. I'll put the emphasis on Pandas, but I'll show you both so that you can compare. And I'll do that on the exact same running example. So I won't go through all the details of the Polars implementation, but I will show you both approaches so that you can compare, and then later on at your leisure you can literally compare the two notebooks with one another and see which style suits you best. In fact, if I were to scratch and all other things let's say put to the side, personally I do prefer the Polar style because it resembles much more the let's say classic SQL, so SQL way of thinking. And this is something that, let's say, I grew up with, and that's for me much more natural than the million of API functions that Pandas defined to do essentially what SQL already did quite well, let's say 4 decades ago. So in that respect, Polars resembles the way of thinking of SQL a bit better, and hence all else excluded, and that would be a motivation for me to use Polars. If you start out from scratch, you don't have any legacy Pandas code, you don't have any code yet, you have a fair choice between either Pandas or Polars, but still getting help, finding information, finding tutorials and so on, Pandas still has the edge by quite a margin. So that's, again, something to take into account. It's non-trivial. So let's start with Pandas. So basically, it's been designed for data science. It should not come as a surprise. And of course, like any library, it defines a number of things. It defines data structures. And the two important data structures in Pandas are the series, so that's for one-dimensional data, and the data frame, which is for two-dimensional data. Back in the old days, you also had a panel for three-dimensional data. Apparently that was useful in the financial sector. I've never seen, to be honest, an example in science. Well, okay, in non-financial science, let's rephrase. And anyway, it has been taken out of the library a while ago. But yeah, it's just to put some limits on what can be done with Pandas. And then, of course, on the one hand, you have the data structures. On the other hand, you have algorithms. And there are lots of algorithms built into Pandas on top of series and data frames to select data, to reshape your data, to get a different view on your data, for instance, using pivot operations and so on. And then, of course, there are quite a number of utilities. And for instance, some level of visualization is built in, and some, let's say, higher level operations are defined on top of that. That can be useful. You can also just use libraries which you're already familiar with. For instance, you can happily use Matplotlib. There's no problem with that. I'll not talk about Matplotlib today because I would prefer to mention on the one hand Seaborn and on the other hand HoloViews, which are different approaches to visualization in general, and for Seaborn are, in the context of data science, perhaps a bit more interesting than pure Matplotlib. Okay, so essentially, depending on which version of Pandas you're using, it's backed by either NumPy or PyArrow, and both of them ensure that column data, because that's what it's actually about, column data is represented, is stored in memory in a very efficient way. Okay, so basically it's very nice to use Pandas in order to experiment with data, especially in conjunction with Jupyter Notebooks, where Pandas data files are rendered in a visually appealing way. Okay, so for those of you who come from our background, essentially our data frames were the source of inspiration for Pandas data frames. So basically the developers really had a good look at our data frames, were jealous it didn't exist for Python, and decided to develop Pandas. Okay. So just as for NumPy, for instance, you would import NumPy SNP. That's the traditional thing to do. That's what you always find online. For Pandas, we've got a similar thing, import Pandas SPD. Okay, so I'll always do that. I'll always assume that this is done on the slides and so on. Okay, so rather than following the slides, I'll switch to a Jupyter Notebook in a minute in order to consider a data exploration use case, which is based on this Excel spreadsheet, and also another one which I'll talk about later. So I'm assuming an experiment, The experiment is from life sciences. So there is a group of patients. Each patient is identified by a number between one, from 1 onward, let's put it that way. And basically, at a number of time points, the temperature of that patient has been measured, and that patient has been administered a dose of a certain drug at that point in time. So that's our data set. So it's in long format in the sense that each row represents a patient and a time point for that particular patient. So that's the data format. It's stored in Excel because unfortunately that's one of the data sources which you have to deal with quite a bit. Okay, I'll switch to a Jupyter Notebook now. So I'll launch. Zoom it a little bit. Okay, I'll launch a Jupyter Lab session. Yes, maybe before I do that, let me show you this. So basically, all the software which is required in order to run the notebooks in this source code directory is, let's say, formalized as an environment YAML file. So to create a Conda environment, or more precise, this spec file, which is for Linux only, but the environment file would allow you to actually create a Conda environment on a Mac, on Linux, or on Windows even. So that would work. So this is quite convenient because it allows you to run almost all the notebooks in this presentation. Not quite all of them. There is a very recent one for which the environment is not updated yet, because I'm unsure whether I want to do that, because it's cluttering the environment a bit. So, yeah. Okay, let me start Jupyter Lab. It's going to pop up somewhere. This is convenient. Okay, I'll just detach this. That makes it a little easier to deal with. And this I'll need for a while. Let me go to Pandas. Okay, and then I need to find the right presentation. So that would be most likely this one, because the problem is there is patient and there is patient data. Patient was the original notebook for the slides on Pandas in the presentation, while patient data has been extended significantly. So that is the current one. Come on. Okay. So let me collapse this now. Let me increase the size a little bit. Okay, it's always a compromise between, on the one hand, screen real estate and on the other hand, legibility. So, okay. Just the requirements. Basically, what do we need? We need a bit of visualization, which in this case is done both using Matplotlib, but mainly with Seaborn. We need NumPy, we need Pandas, and okay, the Matplotlib inline thing here, Magic could actually be omitted because that's no longer required. Okay, so let's load all the dependencies. So as I already mentioned, I already described the experiment. So the first thing to do, of course, is to load the data. And that's one of the things where Pandas is really quite convenient. It has quite a number of read methods or read functions that query a data source and will return a Pandas data frame. So for instance, there is a read Excel function that just takes the name of an Excel function, and of course it has a million optional arguments, for instance, to control which worksheet in an Excel workbook you want to use, etc., etc. So this is a rather simple Excel file. It just contains a single sheet, so I don't need to specify anything special. Okay, so I will get a data frame when I execute this. And one of the things you typically want to do as soon as you've imported some data is to actually check that a little bit. And there are a couple of functions to help you there. And one of the nice ones is in fact the info method. And that gives you an overview of what is in that data frame. So let's have a look at it. We have a range index. So in total, there's 62 entries. Okay, they will be indexed by numbers from 0 to 61. Again, total 62. Then there are a number of columns, in total 4. And then we get a list of all these columns. So under the column heading, we have the name of that column. So it's patient, dose, date, and temperature. Not a big surprise. And then we have the number of non-zero entries in those columns. So that's 62, 61, 62, and 61 respectively. Okay, that's interesting because that already tells us that most likely there is missing data. Because in an ideal world, these four values would all be equal to the number of rows, 62. Given that that's not the case for dose and for temperature, that means something is off. So that's something that we will need to take into account later on. And then let's have a look at the D types. So basically these are the types of the data, the types of the columns. So each column has a uniform data type, and that's called a D type, which is very similar to how NumPy would call them. And as you can see, the patient ID, as you will remember, that was an integer starting from 1, is encoded as an int 64. So essentially, a 64-bit integer, so an 8-byte integer. That means we have integers between 2 to the power minus 2 to the power 63 and 2 to the power 63 minus 1. So yeah, we can treat lots and lots of patients here. We will come back to these data types later on in quite a bit more detail. Then we have the dose, and as you can see, that's a float. It's a float 64, so basically that means 8 bytes to each element, and that means double precision. Double precision means 15 significant digits, numbers that range up to 10 to the power 308. So basically, those are quite large numbers. Okay, then there is also the date, and as you can see, the read Excel function has done the right thing automatically. It detected, or it read from the metadata in the Excel sheet, that this was indeed time information, date time information, and it encoded it as date time 64. And that gives you nanoseconds precision, which is of course a bit over the top for this type of experimental data, but who cares? And then we have the fourth column, and again, that's float 64. It encodes the temperature. Okay, so then you get an additional list of the D types, just the summary information, and also interesting, and we'll come back to that later as well, the memory usage. In this case, a very meager 2 kilobytes. So yeah, that's clearly a very small data set. So that is a very useful function to run, and it gives you a very good idea of what your data looks like. Okay. Other things to quickly explore a data set is the head method, and that just gives you the 5, or if you specify an argument, the number of lines at the top of the data frame which you are dealing with. So by default, just 5 first rows. What I always find a good idea is, besides looking at the head, also look at the tail. And as you can guess, that is going to give you the 5 last lines. And this I typically do because if there is any trouble with reading data, it often happens at the end. So it's always a good idea to check the last line and to see whether that makes sense. In this particular case, everything seems fine. This seems like a regular line, no problem there. Okay, so another way to get a handle on your data is to use the describe function. And this is also a quite useful one, because it will give you, for numerical data, in the broad sense, it will give you statistical information. So it's descriptive statistics. So you get the count, okay? This we already had with the info command, but still it's useful to have it here. The mean value, the minimum, the maximum, the percentiles, and the standard deviation. So that's quite useful. Of course, it doesn't make sense to compute the mean value of the patient ID. That's a bit silly. It also makes very little sense in this particular case to compute the measures for the date, but you get them for free, so essentially who cares? Why is this useful? Well, basically, you might want to check, for instance, the minimum and the maximum value for the temperature. Because suppose you would see a minimum value which doesn't make medical sense, for instance 0 or 12 degrees or something like that, yeah, then you already know that something fishy is going on with your data. In this particular case, the temperature ranges from 35.9 up to 40.7. So if the temperature is indeed expressed in degrees Celsius, then this makes a lot of sense and the data could be sane. Similar for the dose. If we would get a negative value for the minimum, that would be rather odd. If the maximum value would be ridiculously high, again, that would be an indication that maybe something is off with our data. So again, that's one of the things that I do when I get an unknown data set or a data set I have my doubts of. I check the description, the descriptive statistics, in order to see what that data set looks like, what the values looks like, whether things make sense. Okay, so one of the things we would like to know is how many patients are we in fact dealing with in this particular data set. We already know that it's not going to be much, but okay, let's have a look. So what can we do? Well, we can use the data frame, and then we can select the column patient just by using dot notation. So there are two alternatives. I'll show you the next one in a minute. And then you can do, you can apply the unique method, and that is just going to give you a series consisting of the unique values. Okay, we print that, and basically, as you can see, we get a range of numbers between 1 and 9, and we have a total of 9 numbers. So basically, we have 9 patients in our patient group. I could have done that differently, in the sense that I could have done experiment data, and then the column name simply specified as a string. So this looks very much like you would use a Python dictionary. So essentially that allows me to access a column as well. Which one to use is a bit up to you. It's on the one hand a matter of style, and on the other hand it also depends a little bit on what you're doing. So again, we get an array consisting of 9 elements. Okay, so the result is the same thing. Okay, so one of the things which we might want to know is, do we have the same number of measurements for all the 9 patients? Okay, so we're not interested in the dose, we're not interested in the temperature. We're only interested in the columns patient and data. And those we can select using this somewhat bizarre looking notation. So essentially, the outer brackets are used to select the columns. The inner brackets are just a Python list containing names of the columns we're interested in. So this creates a new data frame that consists only of 2 columns, patient and date. So no dose, no temperature. Okay. And then we want to group by patient. So essentially that means we will have 9 groups consisting of the number of measurement points in time for each of those patients. And those we want to count. So we will get a count for patient 1, we will get a count for patient 2, etc. Okay, so if we do that, you see we get 7 counts for patient 1, and so on. And patient 6 only has 6 counts rather than 7. Okay, so basically there is something going on with patient 6. Okay, let's have a look at a patient which has 7 entries, and let's just check how many let's just check the date time information for the measurements for that particular patient. How do we do that? Again, we start from our data frame, and then we have got this somewhat, or rather very bizarre looking thing. So we have .log, and the odd looking thing is these square brackets here. Okay. Let's first look at what the square brackets contain. So essentially, it's experiment data, patient equal to 1. So what I'm doing here, I'm selecting the rows where the patient entry is equal to 1. So I only want the information about the first patient, or patient with ID 1. Okay, what's the deal with this rather odd-looking .log? Well, essentially, you might think .log is a method on a data frame, but no, it isn't. It is in fact an attribute. So .log is in fact an object. It's a location object, which you can index. And that's exactly why there are square brackets here rather than the normal braces, because it is selecting out of an object rather than a function call. So that explains that. Okay, so again, using the .log object and my selection criterion, I get a new data frame with only that information, namely the information on patient 1, and I'm interested only in the date column, so I select that again with .date. And then you see that the measurements were done on the 12th of, the 2nd of October in 2012, and they range from 10 o'clock in the morning to 4 o'clock in the afternoon. Okay, now we can do the exact same thing obviously for patient 6 and compare, and then you see that in this case I'm just selecting everything, so I'll get the patient, the dose, the date, and the temperature in this particular case, and you see that the information which is missing is in fact the measurement at 4 o'clock in the afternoon. So the last measurement for this particular patient was at 3 in the afternoon. Okay, that may have many reasons. The person might have left the hospital, whatever. So basically, we don't know. But yeah, that is missing data. Okay, we will see how to deal with that later. Okay, so that's at least one source of missing data. One thing perhaps important to mention, so of course this data set was completely made up, and to be very clear, this does not seem to be the way you do experiments on humans. Someone once told me, okay, if you do experiment this way, you kill people. So no patients have been killed in order to get this data. This is just made up. So view this as, let's say, a training on how to visualize data, not a training on how to set up medical experiments. I don't know anything about it, and fortunately I don't have to do that. So basically there are people specialized in that, and for instance Frames is giving quite a number of trainings on how to set up experiments in an ethical and let's say a proper way in order to do experiments on, well, in a biomedical context. Okay, so As you can already guess, this is in fact time series data. But as the data is represented now, it's a bit annoying because we have this very long table with patients and data and date information, and it's very hard to spot deep trends here, to visualize this as something that is time series data. So we somehow have to transform our data into a different shape that makes it much easier to analyze. And this is where the pivot function or the pivot table function is quite useful for. So again, I start from my data frame which I read in, and I'm going to produce a new data frame with the name time series. Okay. So the pivot table function allows me to reshape my data to get a different view on my original data. So I want a new data frame, and the index of that data frame should be the date. So basically each row in the new data frame is going to represent a point in time. So hence index is date. And then as columns, I want patient. So when I execute this, you see that I indeed get a new data frame. And what we have, the screen is a little bit too small here, or too narrow to be precise. So basically, I now have a two-level columns. So this is the dose column, but at a sub-level, there is a column for each patient. And as you can see, patient 1 got 0, well, everyone essentially didn't get anything administered at the first point in time, but later on, patient 1 got a dose of 2, patient 7 got a dose of 10, etc., etc. So, as you can see, the date here is printed in bold. That's because it's the index of our data frame. Because on the one hand, the data frame has columns, those contain the data, and on the other hand, it has an index, and that can be any number of things. Let's perhaps quickly go back to our original data frame. For instance, this one here. As you can see, there is also such a column printed in bold, and that's the index of the original data frame. So basically, those are, if you will, the row numbers of the data in the data frame starting from 0. So essentially that means that in my original spreadsheet this would correspond plus or minus 1 to the row number in that spreadsheet. So that's the default. The default is always just a numeric index ranging from 0 to something, and you can have a different index, for instance, in this case, the date. So now, basically, a row is for a specific point in time, for a specific date. Okay, so I talked about the dose column and its subcolumns per patient. We have obviously the same thing for temperature. We have the same thing for temperature. So let me try and, oh, that was bad. Let me try and shift this a bit. Here's the thing I want. Yeah, this is awkward, but you see that indeed there is a temperature column here, again ranging from 1 to 9 for each patient, and you see the initial measurement of the temperature of the patients. Okay. So now I've got a data frame time series that's much more amendable to that. This is really inconvenient. Okay, which is much more amendable to analysis, to consideration as a time series. Okay, now I can very easily visualize things as time series by, for instance, visualizing the temperature column. And that's, as you can see, very, very easy. I just select the temperature column, and I use the plot method. And what I get, without any further ado, is a very decent plot. I get the date on the x-axis, and because that's the index, and on the y-axis I get the temperature, I get a legend color-coded for each patient. So as you can see, with zero effort, I get a plot that is, I wouldn't call this publication ready, but for a quick data exploration, for data analysis, this is quite useful. So this is one of the things which I like about Pandas. It's very easy to visualize things. And that's also something where Polars is in fact lagging behind. It doesn't have these built-in visualization capabilities. Is that a showstopper? No, because there are many ways to visualize data. So it's not a showstopper, but yeah, for a quick analysis, this is really nice. So if you look at this in detail, you may notice a number of things. One of the things which you should notice, but the problem is that the plot is so busy that you can hardly see it. But actually, if you look at the data for patient 6, that would be this brownish line here. And as you can see, it probably ends here. We can't be really sure, because basically it might be that the yellow line is just, the orange line is just printed on top of it. So we're not quite sure, but we know that for patient 6, this data point here, the one for 4 o'clock in the afternoon, would be missing. So it's visually not clear, but yeah, there's a strong indication that that is indeed the case. However, if you look closely, you also see something else. You've got this green line here, and the remainder of the green line there, and something seems to be fishy at 1 o'clock in the afternoon. 4 green, who is that? That is probably patient number 3. So basically something is wrong there as well. So let's have a closer look at the data for patient 3. Okay, again, we can just use that plot method, but now we use we select the temperature only for patient 3. Okay, and then you see that indeed a point is missing at 1 o'clock in the afternoon. Okay, something that I should remark upon, because it's really non-intuitive. It's counterintuitive. So you see this 3 here, and it's just a number, it's an integer. That's a little bit weird in multiple ways. So one of the things that you might think is that it actually refers to the sub-column of temperature at index 3, if you think in terms of lists, so basically the 4th column, and hence the data on patient 4. But that's not the case. 3 in this case is the actual column. Okay, but that again is weird or counterintuitive, at least for me, because this basically means that column names or column identifiers, I should say, are not necessarily strings. Temperature is a string, 3 is an integer. So a column name, I hesitate to use the word name, can in fact just be an integer. So that's something that you need to take into account and that you need to realize, because at least for me, yeah, this is pretty counterintuitive. But yeah, if you know, it's not an issue. And at the end of the day, it makes your life easy because you don't have to think in terms of indices, you don't have to put quotes here or whatever. It's just the name of the column if you want. Another thing I forgot to point out with the previous plot, but no problem, I can do it here. As you can see, this plot method is pretty smart, because it noticed that the range of dates was such that it was enough to just print the time, and it didn't bother to print the actual date, because there is no change anyway. So in a way, it filters the information in a very useful way. It tries to eliminate clutter, and it only shows what's, at least what it thinks, is required in order to interpret this data effectively. Okay, so there is missing data. That's pretty clear. Here's an example. So, okay, let's have a look how to check that. And one of the things we can do is apply yet another method on our time series data frame. And the method we're going to use is null. And you can probably guess what it is doing. So forget about the rest of the expression. So concentrate on the is null. What it is going to do is just return false if the entry in the data frame, so basically the column row, is non-null, so is present, and it will return true if there is missing data in a row, column, cell, basically, of that data frame. Okay. Now that would give me a data frame with a lot of false and trues. Hopefully many false and only few trues, because I don't want much missing data. I want as little missing data as possible. So basically, that would be a bit hard to interpret. So what I want is a summary. I want to know for which points in time there is any missing data. Okay, so I can do that by, to the data frame, applying the any method. And that is going to summarize data. I do have to specify the axis, and in this case, axis is 1. What does that mean? Well, for those of you who are familiar with NumPy, you know that there is a notion of axis in a multi-dimensional array. So basically, if you have a one-dimensional array, there's only one axis, and that would be axis 0. If you have a two-dimensional array, on the other hand, you have two axes. You have axis 0 and axis 1. And axis 0 is the rows, axis 1 is the columns. And that's essentially the exact same thing here with pandas. So axis 0 would do an operation row-wise. Axis equals to 1 specifies that I want to do it column-wise. So this will be a row-by-row summary, and the answer will be true when there is missing data for that row, and false whether if there is no missing data for that row. So, of course, just like there is any, there is also all, as you can guess, with similar semantics but flipped. Okay, so as you can see, there is no missing data for 10 o'clock, 11 o'clock, 12 o'clock, but there is missing data for 1 o'clock. This we already knew. But there is also missing data for 2 o'clock. This we didn't know yet. And then there is also finally missing data for 4 o'clock. Okay, we already knew that because we knew that patient 6 wasn't in the experimental data at 4 o'clock. Okay, so we discovered a few new missing data points. A thing about missing data which I want to mention and detection of it, there is also a package that allows you to visualize that as kind of a heat map. So you get your entire data frame, and you would get, if memory serves, white dots for missing cells and black dots for data that is actually present. This can be useful, not so much to detect missing data, but more to spot patterns in missing data. And that can sometimes be quite useful during a data exploration phase, because it might show you some hypothesis for why this data is missing visually immediately, rather than you having to check what might be the cause of certain missing data. For instance, you might notice immediately that during a given time point or time range, that certain sensor data is totally missing. And that might indicate that that sensor was temporarily malfunctioning, or that something was wrong with the network connection, connecting it to the data aggregator or whatever. So that is very useful, but mostly to spot patterns, not to detect missing data. Because visually, you just might miss a single cell. It's just one pixel, so basically it's very easy to miss. So I wouldn't recommend it for that purpose, but for spotting patterns, it's great. Okay, then, of course, we need to have a look at the missing data which we discovered at 2 o'clock. So let's have a look at at 1 o'clock in the afternoon first. So we already knew, in fact. So basically, we're going to query our time series data frame, again with the location object. And in this case, we just specify the exact point in time. Notice that this is, in fact, very convenient. And you might say, yeah, okay, this looks pretty straightforward. Why are you commenting on this? Because basically, if you're familiar with how, for instance, the date library or the date module in the standard Python library works, then you know that if you want to query a time or if you want to compare times, that you have to jump to quite a number of loops, of hoops. That's not so very easy. You have to construct a date object, and then you can compare, etc., etc. It's a bit of doing. So here it's really intuitive, and that's a nice thing. That's why I want to point it out, that this is a very nice design. So basically our index is a date time thing, but I can simply specify a string, which is then automatically, by this indexing function, converted into a datetime object and compared to the entries in my time series data frame, well, the index entries. Okay, so basically I get the data for this particular point in time, and you see that for each patient there is a dose. That's not a problem, but for patient 3 there is no temperature information. Okay, no surprise, we already knew that. We had already spotted this in the plot, but then again, it's good to confirm. And then, of course, we can do the exact same thing for 2 o'clock in the afternoon. And then you see that there is missing data, in this case for patient 4, and for some reason the dose was not recorded there. Okay, so good. Let's have a look at that. So again, time series .dose in this case, because we're interested in the dose column, and the column for patient 4. And we can simply plot this. And then you see that indeed there is a point missing at 2 in the afternoon. Okay. Now, how to deal with missing data? There are very many ways to deal with missing data, and what you do exactly depends on the circumstances. So there is no silver bullet. It depends on what your data represents, how you deal with missing data. One way to deal with missing data is just leaving it out. That's one way. You may want to do that. It may be the best way of doing that for some definition of best, which I can't give you a good one of, because again, it depends on the situation, it depends on the domain, it depends on the data, etc., etc. But sometimes you don't want to just omit that data completely, either because you have a small data set or because you know how to deal with it in a reasonable way. Okay, so then there are a number of things you can do. For instance, you can say, well, okay, I will replace all the missing data by a certain value. Okay, that might make sense. You might also say, no, that's not what I want. I want to be a little bit smarter. I want to do an interpolation between the neighboring points for that missing value to determine the value at that point where the data is missing. And of course, here in this case, that might make a lot of sense, because if I do a simple linear interpolation between these 2 points, I would end up with a dose of 0 for 2 o'clock in the afternoon, which, given the data, seems quite reasonable, as the patient didn't get any drug administered at 1 o'clock, at 3 o'clock, and at 4 o'clock. So it's not unlikely that just doing a linear interpolation isn't a bad idea. Okay. There are other recipes for interpolation. So basically, linear is the default, but there are other interpolation algorithms. For instance, you can do a quadratic interpolation, you can do a cubic interpolation, you can do splines, etc., etc. There are many methods which you can specify using the optional argument of the interpolate method. So in this particular case, I'm going to experiment a little bit. I take my time series experiment, and the data frame. I select the temperature column and the data for 3. Is there a question? Because I heard a ping, which usually means a raised hand. Okay. No raised hands. Okay, then I don't know what the beep was. Let's continue. So basically, I select my data, temperature data for patient 3, and I just apply the interpolate method to it. So that gives me a new series, and I just store that into interpolated 3, and I do the exact same thing for the dose of patient 4 and store that in interpolated 4. Okay, visualizing that, no surprises. So for the temperature, this point was missing, so at 1 o'clock, and as you can see, a linear interpolation between 12 o'clock and 2 o'clock has been done. Seems reasonable, might be what you want, might not be what you want, depends on the context. So I would say, yeah, what to do, again, there is no silver bullet for that, so basically you have to kind of do what makes sense in your specific context. And then, of course, for the missing dose, indeed, now at 2 o'clock, the dose is set to 0. Okay. So now I have 2 series, one for the temperature of patient 3 and one for the dose of patient 4. But of course, my original data frame is still unchanged. So I can just do that interpolation, and I'm going to do that in place. So basically, up to now, each and every operation I did on a data frame produced a new data frame with either part of the data or the entire data or whatever. So in this particular case, I'm not going to do that. I'm just going to do this in place, because I don't want to assign a new to a new data frame. I just want to continue working with time series, but now with the data interpolated. So there are quite a number of methods which you can apply to data frames, which have this in place optional argument. And as you can guess, if I specify that, the data frame is in fact modified in place rather than a new being created. Okay, so of course now we can check whether there is still missing data, and of course it's the same query as before, so there's no surprise here. But now everything is false, so there's no missing data. Then of course the interesting thing is, because we've been talking about the missing data for patient 3 and 4, but there was also missing data for patient 6, and as you can see, it's no longer missing. So something has happened. Interpolate has done something in addition. So let's have a look at that data for our patient 6 now, and in this case the temperature. And as you can see, the thing it has done by way of interpolation is just take the value for 3 o'clock and use that for 4 o'clock. So essentially, if there's missing data at the beginning or the end of a column, then interpolation just means replace that missing value by the neighboring value, either backward for data missing at the start of a column or forward for the data at the end of a column. Okay, and of course similar for the dose. Does that make sense? Again, maybe yes, maybe no, but this is what Pandas does by default. Okay. Now, we have been working with the data we had. We transformed it into something which is more appropriate to time series analysis, but it's still the same data as we had before. So one of the things we can also do is to add new columns to our data frame based on whatever. Essentially, in this case, we want to compute something. So one of the things that might be interesting is to consider the average temperature at each point in time over all the patients. So I want an average temperature for 10 o'clock, 11 o'clock, etc., averaged over all the patients at that point in time. Okay, computing that is pretty straightforward. We have our time series data frame. We select the temperature column. That means, of course, that column, but its sub-columns as well. So basically, the sub-columns for patients 1 through 9. And we compute the mean value. And again, we want a column. We want an average for each row. So basically, that means that we have to specify axis is equal to 1, because otherwise we would get something different. Then we would also get average temperatures, but for each patient over each point in time. So basically, we would get something different. So this is a row-wise mean value. Okay, and once we've computed that, we insert that into our existing data frame as a new column, and that new column has as name average temperature. Okay. As usual, of course, column names can have spaces, but I would not recommend you to do that unless you have a very, very good reason to, because basically it makes your life a bit more difficult. It makes your life more difficult in the sense that, of course, you can't use that dot notation easily. So basically, then you always have to use the square brackets and the indexing, which you may or may not like. It's up to you. But typically, I consider it good practice to have column names without spaces or special characters. Okay, so we can compute that, and then we can plot this. And as you can see, that would, okay, where's my, that would be the usual way. Now time series has a new column, average temperature, so I can simply apply the plot method to it, and as you can see, I get this plot. So on average, the temperature of the patients increases and then decreases. Okay, great. No, not much surprises there. Okay, then what also might be interesting is the cumulative doses. There was a question in the chat, sorry. Let's see. Yeah, okay. Look it up, yes. Yeah. Yeah, so ethical guidelines, it is, that depends on your data. So in general, Again, it's very difficult to give you general advice. So it strongly depends also on the culture of your domain, and on, let's say, what's at stake. So suppose that I'm measuring a system, a temperature sensor, I have a pressure sensor, I have some other sensors, potentially many of them, and one is malfunctioning. Okay, so that means that my data set is non-optimal. What do I do? I can say, well, okay, this sensor was malfunctioning. I throw away all the data of that particular sensor. That's an option. And that would be the right thing to do. But on the other hand, if I have partial information, correct information from this sensor and some is missing, that might be quite expensive, because I may not be able to rerun my experiment. For instance, if I'm analyzing data in an industrial setting, I can't just rerun that production run. I can't do that. That's just not possible. If it was data from a space mission, I can't redo the space mission. So in that case, what should I do? I should maybe interpolate or deal in a creative way, let's put it that way, with the missing data. From an ethical point of view, what should I do? I should definitely mention in each and every publication, based on this data, what I did and how I did it. That is the ethical thing to do if you interpolate. If you say, well, okay, I'm working in an experimental setting and data is missing, I messed up, okay, I just do it again, and that is not prohibited by cost or by time or by circumstances or whatever, please do so. Because if data is missing, something is, as you put it, fishy, and I definitely agree that something is fishy. So if you can avoid working with missing data by reproducing your experiment, in this case with the data, then of course that's the better approach. So if you decide to deal with missing data, then you have to say how. Omitting it is dealing with it. Interpolating is dealing with it. Putting some value there is dealing with it. So that means in any case, whatever you decide to do with it, you have to report it. That's the ethical thing to do. And that's the general advice. If you manipulate your data, on the one hand, you have to document it. On the other hand, it has to be done in a reproducible way. So those are the ethical things to do in any circumstance. Whether it's then methodologically correct depends on the domain. And yeah, suppose you submit an article and you say, okay, I dropped that part of the data because there was missing data and I interpolated this and this and this. It might be that your paper is reviewed and that the reviewer says, well, okay, yeah, I don't accept this. This is methodologically wrong. Please redo the whole thing or go away or go do something else. So yeah, that depends. So reporting is crucial here. Reporting on the one hand, being able to reproduce the whole workflow on the other hand. That's the crucial thing anyway. I hope that kind of answers your question. Yeah, okay, apparently it does. All right, so yeah, what also could be useful is adding the cumulative dose for each patient. So basically that would be the dose at 10 o'clock. Then for 11, that would be the dose at 10 o'clock plus that at 11 o'clock. For 12 o'clock, that would be the one at 10 o'clock, 11 o'clock, and 12 o'clock, the sum of that. Okay, so that would be the cumulative sum. Okay, so we want to do that for the dose, and we want to do that for each patient. Okay, so we have a simple for loop. and we have the dose column, and we want all the columns in dose, so that would be column 1, 2, 3, 4, 5, etc., one for each patient. Okay, then we can compute the cumulative dose, and that's quite simple. That's the time series, the dose for the patient, and we compute the cumulative sum because there is such a method built into Pandas, so that's easy. Okay, and then I create a new column, cumulative dose, with a subcolumn for each patient. So basically, just like dose would have subcolumns 1 to 9, cumulative dose will also have columns 1 to 9. Okay, I could do that in one go. I just split it up because otherwise it gets a bit too long. Okay, so when we do that, we can create a plot of the cumulative dose, and of course we will not get a single line, we will get 9 lines, one for each patient. Okay, and as you can see, it's quite reassuring that the cumulative sum is actually, in this case, a monotonous function, because we know that all our doses are positive, strictly positive, well, not strictly positive, larger or greater than 0. So essentially we expect monotonic functions here, and that's indeed exactly what we get. So that's reassuring. Again, no surprises. We automatically get the legend, blah, 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 the whole thing. So no surprises here. Okay. So what might be interesting is to have a look at the maximum temperature and the total dose. Because, for instance, it might be that the total dose depends on the maximum temperature. And this, according to people who know, is where I'm actually killing people, apparently. Okay, I'm very willing to believe that. Again, I don't know anything about experiment design in this kind of setting. I just need data. So we want to reshape our data again. And again, the pivot function, or in this case the pivot table method, is going to be very helpful. So in this case, we want our data per patient. So the index is going to be the patient. And the values which we want are the dose and the temperature. But we don't really want the dose and the temperature, we want aggregate values. So for the dose we want the sum, and for the temperature we want the maximum. So for each value we specify which aggregation function should be applied. Sum for dose, max for temperature. Okay, and as you can see, we get a new data frame. In this case, the index is the patient, and we have two columns with dose, the cumulative dose, I should say, the total dose, and the temperature, in this case, the maximum temperature. Okay, so we can do, let's, for the sake of the argument, in this case, not do a line plot, but a scatter plot, just to show you that you can do some more sophisticated plots as well. So basically, we have hypothesis, plot, and then scatter. So this is going to be a scatter plot with on the x-axis the temperature, on the y-axis the doses, and we also specify a marker. Lowercase o means a big circle, essentially, or a circle if you want. I could do something else. I could do, wait, did I evaluate this? Yeah, I think I did. Okay, so basically I get these circles, and well, this kind of looks like somewhat linear relationship. So maybe there's something to our hypothesis that in fact the total dose is related to the maximum temperature of the patient. Okay. So this is where we can use Seaborn, because Seaborn can do a similar visualization, but quite a bit smarter. So basically we imported Seaborn as SNS. Okay, for those of you who wonder why on earth that's SNS, well, basically it's a joke. It's a pun because Seaborn is the name of a fictional character of an American president in a sitcom, The West Wing. And his initials are in fact SNS. So the last S is for Seaborn. I don't remember what his first and middle name are, but his initials are SNS. And hence, this is let's say a pun on that. So hence, import Seaborn as SNS. So SNS. Now we have LM plot. So LM for linear model. We specify the x-axis, the y-axis, and the data frame out of which this is taken. So basically we have our hypothesis data frame, so no problem. What we get is a very nice looking plot with temperature and dose, and the linear regression line here, and also a blue shaded region, which is an indicator for the certainty of this linear model. Unfortunately, it's not possible to get out the numerics of this. So basically, you don't get the slope, you don't get the intercept for the data. That would have been quite convenient, but unfortunately, that is not implemented. Okay, of course, if you want that, there is always SciPy with the Lindgress method, which will nicely give you all these parameters and all the quality measures and so on. But for quick visualization, this is quite useful, and indeed it seems to sort of support our hypothesis that this might be a linear regression. Again, of course, you need to do a bit of statistics in order to justify this, some hypothesis testing, etc., etc. But let's not go there. That's not the subject of this particular training. Okay, this might be a natural point to have a break, because now we're going to continue the experiment, but we're going to use an additional data set. So it's of course related to the data we are considering now, but now we need to combine essentially the information which is in two spreadsheets. But before going into that, I suggest we have a break of, let's say, something like 10 minutes. So perhaps till 10:35. I'll put that on the whiteboard. Okay. But just before we go into the break, are there any questions? I'll ask again after the break. But if there are any, feel free to type them in the chat. So no problem there. Okay, let's resume. I'll share my screen. Okay. So, the second part of our dataset is again an Excel spreadsheet. And of course, we know how to read that, so that is not particularly exciting. But as you can see, it contains data, again, the patient ID, the gender, and a condition, whatever that is. Wait a minute, but never mind. So basically, of course, what we assume here is that the patient's ID between the experiment and this metadata correspond, so that patient 1 in one dataset is the same patient in the other dataset. That's the underlying assumption. And yeah, since I created the dataset, that actually also happens to be true. So let me switch to the chat. Okay. All right, but the question is, of course, is there missing data? So are there any patients in the experiment for which we don't have metadata, or vice versa? Do we have metadata on patients that did not participate in the experiment? So that's, of course, something we don't know. Of course, we can just look at the data and then you immediately see that we have 10 and 11 here, which were not IDs in the original set. We're missing 4 here, so okay, we can visually inspect that easily. But of course, yeah, that's true for a very small data set, and that's definitely not true for a large data set. Also, if you just look at this, then the question is, which values can we have for gender? Which values can we have for condition? So we don't know, but we can count. So basically, what we can do that in many ways, and I'll show you a different way later on as well. But basically, for each of the 2 columns with categorical data, I just specify the names. We get the value in that column, and we drop all the duplicates. And values is going to turn that into a list, essentially. And then we print that, and we also print the list, the length of that list. And then you see that we have for gender the values M and F, so 2 in total, for condition A and B, 2 in total. Okay, so that is quite convenient. However, we can also do something a bit more, how shall I say, we can do that a bit easier. So basically we select out of our data frame the columns gender and condition, again with this weird looking double square bracket. First square bracket select, second is just a list as an argument, and we again use the scribe method. But as you can see, for categorical data, the scribes give you something quite different. So basically, you get the count. That's of course very similar. You also get the number of unique values. And indeed, we already knew that there were 2 values for gender, that there were 2 values for condition with this set of experiments. With this set of patients. And you also get the top. So basically, it means there are more male patients in our patient database than there are females. There are more people with condition B than with condition A, and you get the frequency of those. So basically, 6 out of 10 patients were male, 6 out of 10 patients had condition B rather than A. Okay. So then what do we want to know? We want to know, for instance, which patients are male and have condition A. So basically that's again selecting. So how can we do that? Well, basically, again, we use the log object, and we want to ensure that the gender is male, so M, and that the condition is B. It's A, sorry. So this might look a little bit weirdish, so let's break it down a little bit. So the braces here, the round brackets, are required. That's because this ampersand operator here has a higher priority than the equality operator. Otherwise, you get errors that you are combining things which cannot be combined. So basically, don't forget the braces. They are required. And of course, as you can guess, the ampersand stands for the logical AND here. Represents the logical AND. It's not a logical AND in this case, but okay, bear with me. So basically, that means I want to generate all the rows in my data frame for which the gender is M and the condition is A. Okay, so doing that, indeed, you see you get a data frame with 3 patients, 1, 3, and 5. They are, of course, all male and all have condition A. And here you see the initials again. So basically that would be the first row in the original data frame, the third row, and the fourth row in the original data frame. Okay, so that's just to show you that you can actually do quite sophisticated queries using, on the one hand, the log object, and on the other hand, composite Boolean expressions. Okay, so what we want to do, of course, is to merge these two data frames, because we have the data frame with experimental data, we have the data frame with metadata for the same patients. So we want to merge that into one data frame. Okay, how can we do that? So basically, the IDs should match. So we can check a little bit. So we can say, well, okay, let's get a set of the patient IDs. And now this is, of course, just Python's set function. So I get the values of the patient IDs in the experiment data. I create a set out of it. I do the same for the metadata. I create a set out of it. And then I can just do set operations. In this case, the difference between two sets. So I can get, if I do patient experiment minus patient's metadata, I get all the IDs of patients that were in the experimental data, but not in metadata. And if I subtract, or if I do the set difference between patient's metadata and patient's experiment data, I will of course get all the IDs for which all the patient IDs for which I have metadata, but no experimental data. And then indeed, this confirms in a more, how shall I put it, in a more structured way, in a more reproducible way, what we already noticed by just visualizing, by just inspecting the data frame visually. We don't have any metadata on patient 4, and we don't have any experimental data on patients 10 and 11. Okay, so of course, this is about the experimental data at the end of the day. So probably patient 10 and 11 are not of interest, because we don't have any temperatures, we don't have any doses. This is what the whole thing is about. So we're probably not that interested in 10 and 11. Okay. So now the question is, how can we combine these two data frames into one? And that would be using the merge function. So Pandas merge function takes two data frames as its first two arguments, and then an argument on, which indicates which column in both data frames should be used in order to combine them. So in this case, they share the patient ID, so I'm specifying the patient column. And then another optional argument says how to do that. And how can be a number of things. So basically, there are 4 options. I can do a join. which basically means that only there will only be rows for which the patient ID occurs in both data sets. Okay, so basically that would give no missing data. That would give me patient 1, 2, 3, not 4, because there's no metadata, 5, 6, 7, 8, 9, not 10 and 11 because there's no experimental data. So that would be one way to do that. But then, of course, I would drop patient 4, for whom I do have experimental data but no metadata. Okay, so what I can also do is a left join, and that basically means that I would include all the IDs, all the patients which are in experiment data, so the left argument, if you want, the left operand of the join. So that would include 4, but it would still exclude 10 and 11. Okay, I could also do a right join. So that's similar, only, of course, all the IDs of the right operand, so of metadata, would be in the resulting data frame. So I would get 1, 2, 3, 5, 6, 7, 8, 9, 11. That might make sense. In this case, not so much, because I'm mostly interested in temperature and dose, etc., etc. So yeah, I'm not going to do that. Or I could do a full outer join, and that would basically mean that all the IDs would be there, but of course, missing data, missing metadata for 4, missing experimental data for 10 and 11. So essentially, inner join, least missing data, outer join, most missing data. In this case, since I don't have that much data and I would prefer to keep all my experimental data, even if there's no metadata, I choose a left for how. Okay, and then this is what I get. I get my patient column with the IDs, I get the dose, I get the time, temperature, and of course 2 additional columns now, gender and condition. Of course, for a patient that doesn't change over time, so basically those values are just repeated for each row for a patient. Okay, I need to actually execute this, otherwise we are in trouble. Now, if you look at, and perhaps let me just show you, because that will be better. It's data, isn't it? Yeah. Okay. Let's have a look at the info. And then you see that we indeed have 6 columns now, as expected. Gender and condition have data type, so dtype object. Okay. The object is used for anything that Pandas doesn't really know how to handle, so it's represented as a string or something weird. Okay, that's as such not a big deal, but in this case, gender in our dataset only has 2 values. Condition in our dataset only has 2 values, so that's categorical data. So it's actually better to redefine the type for those 2 columns into category. And this we can easily do. We take the data gender column and we convert the type to category. And we do the same thing for condition. And we assign that to the original columns. So they are essentially get replaced. Okay, so if we now look at the info, you see that indeed we have category and a category for both gender and condition. And that helps a little bit because it makes things like the describe a lot easier to deal with than with objects. There are also other reasons which I will come back to in a different notebook elsewhere. Okay, so this is mainly just to show you it wouldn't make that much of a difference. Okay, so what you will notice, of course, is that there now is a lot of missing data for gender and condition. It seems like a lot of data is missing, but remember, it's just patient 4. So essentially it's 7 values, one for each point in time, which is missing. 55 plus 7 is 62. So indeed, one metadata missing for exactly one person. Okay, so we can again do the count, blah, blah. So basically, the frequency here is now, of course, essentially to be divided by 7, if you want to think of that, and the count as well. If you have to, if you want to think as that of the number of patients, then you would have to divide by 5 here, by 7 here. Okay. So the question is, let's do some queries now. How many patients are involved in our experiment that are male, and how many are female? Okay, so we have the patient and the gender column in our dataset. Okay, then we drop all the duplicates, we group by gender, and we count. Okay, the observed false is to deal with missing data. Okay, so if we do that, you see that we get a data frame with a patient column, and as index, of course, the values for gender, so F and M. And as you can see, there are 3 female patients and 5 male patients. Okay. Another question we might ask is how many patients, or which patients actually, had a temperature higher than 39 degrees Celsius, and when did they have that? Okay, and we also want to see the gender. So again, we select the columns of interest, so that would be patient, obviously. Then, since we're interested in points in time, we need the date. Obviously, we need the temperature, and we want the gender. So we select these 4 columns as usual, and then we select all the rows for which the temperature is more than 39 degrees. Okay, so that gives us this data frame. As you can see, there are quite a number of points in time, but as you can see, the majority for this data is that the gender is male rather than female. There's only 1 female patient that had 2 points in time with a temperature higher than 39 degrees, and all the rest is male. On the one hand, more patients, we have 3, 5, 7, 9, so 4, plus they also had a higher temperature for potentially a longer period of time. For instance, 7 had such a high temperature for 4 points in time, essentially. Okay, so what we can also do is, it's a little bit suspicious how many males we have here. So basically what we want is, we want to formalize that one which we counted previously here. We can actually just formally query. So again, we select the data, each row where the temperature is larger than 39 degrees. So this gives us a data frame with less rows, but the same number of columns. Out of these columns, we select patient and gender. We drop all the duplicates, and then we group by gender, again dealing with missing values, and we count. So essentially, there is indeed 1 female patient that had a temperature during the experiment of more than 39 degrees, and 4 male patients. So we counted that by hand in the data frame, but of course you can also simply query. Okay, so the question is there a difference between the genders? And again, this is not a statistical test, so let's be very clear. This is just hand waving and mainly showing you what you can do with pandas, not how you should test this experimentally or statistically with proper methodology. Okay, so This we already know, we've seen that before. Basically, what we would like now is have, again, our data reshaped a little bit. So what we actually want is some reshaping of our data. And again, we're going to create a time series. So the index is the date, and the columns are going to be gender and patient. So now in this case, we have not 2 levels of columns, but 3 levels of columns. Okay. Then we're already going to do the interpolation for the temperature, the interpolation for dose, etc., etc. So again, the usual, and that ends. Then we end up with this data frame. So each row represents a point in time. Each column represents some data. So this is truncated, as you can see. So there are 9 values here, but they're not displayed. So basically, for each dose, I have male, female. So this is indicated here, and the patient ID is here. Okay, we've got a none here. This is patient 4, so indeed that would be missing data because we don't have any metadata on patient 4. Okay, so again, this is a time series thing. Can I evaluate it? No, but now it is. Okay, so basically, what we now want to do is we want the male, again, the average temperature, but split up by male or by female. Okay, so what I can do is I can simply take my time series, gender series, I select the temperature column, and I select all the male subcolumns. And I compute the mean for each point in time. Again, axis is 1, means over a row rather than over a column. Okay, and I do the same for female, so the only difference between these two is F rather than M here. Okay, so what is this? This is essentially a series. As you can see, it's just a single row. So what is a series? Because I mentioned data frames, what is a series? Well, a series is just a sequence of values, but also indexed. So what makes it stand apart from an array is that it has an index that can be a number, as we've seen, but that can also be something else. Okay, so what I want now is essentially a data frame out of these 2 series. I want to combine it. And this I can do using the concat function, and then the list of data frames, or in this case of series, which I want to combine, and the axis I want to combine them over. I want to put them side by side. So axis is again 1, because it is the horizontal axis if you want, and the 2 columns. And then, because I would get something random, well, okay, not random, but I would get something like column 1 and column 2, if memory serves, as column names. I don't want that. I want appropriate column names. So I change the column names of this data frame into male and female for the first and the second series. Okay, so that's just a bit of data massaging. Of course, this works because the indices of both series are the same. So each series had the date as an index, and this resulting data frame will also have the date as an index. So this is a time series of the average male temperature as a function of time and the female temperature as a function of time. And then, of course, we can simply plot this, and you see that indeed the average temperature of males over time is indeed significantly, I don't know, because that's statistics, but the one of the females seems to be lower. Okay. All right, so let's again reformulate or reshape our data a little bit. So the hypothesis is, of course, that stuff happens with the dose as well. So we should look at the total dose and the maximum temperature, and we would like to break that up according to gender. Okay, so again, our good friend, the pivot table on our data set. Okay, so in this case, we want an index which is both gender and patient. So we already saw that we could have multi-level columns. We can also have multi-level indices. So basically we will have as a first level index, in this case, the gender, and at a second level index, the patient. The rest of the pivot table call is very similar as before. As values, we want temperature and dose, and we want to aggregate over the temperature with a maximum function and over the dose with a sum function. And observe this true. I don't want any missing data here because that would mess up things. So observe this true. Okay. And then you see that we get two indices, top level gender. So the first three entries are the females. Then second level index is the patient. So patients 2, 6, and 8 were the female patients. Patients 1, 3, 5, 7, and 9 were the male patients. This, by the way, immediately shows you that that is most likely an artificial data set, because the genders alternate in a very recognizable pattern. So, well, yeah. We could predict that patient 4, actually, the missing value for that would be female, but okay, let's not go there. So basically, we have the total dose and we have the maximum temperature. Okay. Then, of course, we could make a plot, all that kind of thing, but let's not go there. That's what we've seen before. So another thing which we can do is take into account the condition as well. So basically, this is another example of a query. So basically, we can get patient and condition columns. We drop the duplicates. We group by condition, etc., and we count. So we get 4 times A, 4 times B. This is not so very interesting. It's more or less the same. Why I want to show you this is because we can also have multi-level indices here. So I select data, patient, condition, and gender. Again, we drop the duplicates. But now we group by 2 levels. I group by condition and I group by gender. And then we count. So basically, this gives me a multi-level index. Condition is top level, then gender. We have the count of the patients in the only data column of this data frame. So basically, for condition A, we have 1 female patient, we have 3 male patients. For condition B, we have 2 male patients and 2 female patients. So again, this is sort of very nice that you have these multi-level indices. We already saw the multi-level columns, so that is also something that is missing from polars. So for data analysis, data exploration, Pandas still has an edge on that. Okay. Just to show you that we can also create bar plots. So basically, this would be a plot. I'm not going into the details. It's just essentially adding plot bar to the previous query, and you get the same thing but represented as a bar plot. And you see we have condition A female, condition A male, condition B female, condition B male, etc. Okay. Then sometimes you want to go from numbers to categories because the actual values of the numbers don't really matter. And just by way of example, in a way, we can add the status column to the data. How do we do that? Well, essentially, we are going to use the cut function. And that's the way to go from numerical to categorical data. So in this case, we start from our data set and we select the temperature column. Okay. We define a number of bins. Now, in fact, this is a bit of a, in my opinion, misnomer. You define not the bins, but rather the edges of the bins. So the lowest value is going to be 35.5. The highest value is going to be 43. And so basically we get bins, one for each consecutive pair of values. So basically a normal temperature would be anything between 35.5 and 37.5. Fever would be anything between 37.5 and 39, and high fever would be anything between 39 and 43. So we have in total 3 categories: normal, fever, and high fever, and hence we need to define 4 values for the bins, because we have number of categories plus 1. Okay, so we can compute that, and we can have a look at our data. Note this is the original data frame again. So basically we have the status here. So essentially you see we have 38.3, that's indeed fever. We have 37.3, that's considered normal, etc., etc. Okay, so if you look at the info for the data frame, you see that we have an additional column, status, and that its data type is category. Okay, so cut automatically gives you a series with D-type category, so that is quite convenient. Okay, so we can describe this, and essentially you see the count for status is 61. There are 3 unique values, which is reassuring because we should have normal, fever, and high fever. Most temperatures are normal, and the frequency of that is 27. Okay, so now you might remember that we did a query to find the patients and the point in time at which they had a temperature of over 39 degrees. So essentially that's now the same thing as getting those rows in this data frame where the status is equal to high fever. So if you do that, you get the exact same output as before, but now queried in terms of status of a categorical value rather than a numerical value. Okay. And we can actually also get the patients, patient IDs, which at some point have high fever and so on. So that is exactly the same as before, but from a different perspective, from a categorical perspective rather than a numerical perspective. Okay, so this is somewhat of an introduction to Pandas. There are a couple of more things to tell about Pandas, which I'll do in a minute. But first, are there any questions about this part of the presentation? Okay, if not, let's continue with a few important things about Pandas, and especially if you go to larger data sets. Let me have a look. I think it's this one, if memory serves. Okay. So basically, it's worth to look into Pandas data type, because you have seen already a number of defaults. If you have an integer, it's an int64. That's 8 bytes. If you have a floating point value, that is a float 64. So again, that's 8 bytes. That's all well and nice, but it eats memory. And for a small data set, you don't care. For a large data set, you might actually care, because memory, and that's one problem with Pandas, your whole data set, your entire data frame needs to fit in memory. If it doesn't fit in memory, it's end of story. You can't analyze it with Pandas. It's as easy as that. So sometimes you have to apply a few tricks. in order to squeeze your data into a data frame that can actually fit in memory. And that's typically where data types come in. There is another argument, and that is processing speed. So basically, some data types can be processed more efficiently than others. So that is another consideration. But let's first have a look at our data set. So I'm going to import pathlib and random in order to generate some data. So basically, I create a data file. It's a CSV file. It will have 100,000 lines. Okay. And what will it be? So basically, I'm going to create a number of columns, A up to Z, as far as I can see. But is this the one I'm looking for? Just a second, I'm just going to check. Yeah, this is the one indeed. Okay. And then, wait, what am I doing here? No, these are my categories, sorry. So categories range from A to Z. Then I print the header. Okay, so I've got 1, 2, 3, 4, etc. columns, 8 in total, I think. I print those to the file, and then for each line, I generate either a random number, a random integer, or a random choice out of the categories which I defined. Okay, so that's my data set. Don't do this at home. This is a very quick and very dirty hack. If you really want to do this, use the CSV module in Python. That actually will generate proper CSV, while here I'm just hoping for the best and assuming that I will have a valid CSV file. Anyway, so now I want to import NumPy and pandas, and I'm just going to read the CSV file. And in this case, I don't use read Excel, I use read CSV. Okay. If I check the info for the resulting data frame, you notice that I've got 2 floating point columns, 8 bytes, 4 integer columns, 8 bytes, and then object for 2 columns. Okay. I have 100,000 entries which are non-null. That's good because I had 100,000 rows. And you see that the total memory is now 6 megabytes. Okay, 6 megabytes is not much. If you're dealing with data frames of that size, you really don't worry. Of course, I have chosen these numbers in order to get something that evaluates fast. So if you're really dealing with large data sets, multiply this by a factor of 100, then you are at 600 megabytes. That's going to be more interesting. Then you start to have to think about how you represent your data. So this is just a toy example to show you numbers in a reasonable amount of time. Okay, so the question is, these floating point numbers, should they really be represented by 64 bits? Because that gives me 15 digits of precision. Okay. Let's think for a second about our temperature. So basically, our temperature was also represented as float 64, but that doesn't make much sense, does it? Because they're results of measurements. These measurements, if I'm lucky, are accurate up to 1/10 of a degree Celsius. So I will have only 3 significant digits. All the rest is round off, random bits. So not particularly interesting. So I don't need 8 bytes to represent this. I can happily represent it in single precision, so a float 32, only requiring 4 bytes. That is not a problem. Okay, so if that's the case, then, okay, let me. Okay, so basically, what I can do is convert these floating point columns to float32. Okay, we already know how to do that. That is just using the S-type method with the data type we want to convert to. So in this case, NP float32. Okay. So let's check the info again. And as you can see, we now have one column with float32, the other, which we didn't modify, float 64. And notice that we went from 6.1 megabyte to 5.7 megabyte. So that looks good. Okay, now actually what you can do is do this at once, because now we read in the entire data frame in memory, but then only converted to floating point 32. So you can do that in one go. So you can simply read CSV file and you can specify a dictionary with D types. So the dictionary has the column name as the key and the type which you want it to have, which you want the data to have as a value. So in this case, I'm specifying both for columns float1 and float2, then I want to have them in float32 rather than float64. Okay, so doing that, you notice that indeed the types are as expected, no surprise, and that the memory consumption has gone down from 6.1 to 5.3 megabyte. Okay, multiply this by 100 or by 1000 and it's a bit more interesting. Okay, so then of course the question is the integer type, because of course I can represent integers with 8 bytes, but that's huge numbers. As I mentioned, it's from minus 2 to the power 63 up to 2 to the power 63 minus 1. Those are really, really, really huge integers. Is this relevant? For instance, for the patient ID, do I really need 2 to the power 63? I mean, 2 to the power 31 is 2 billion. So I won't have 2 billion participants in my experiment. So again, maybe we can better use a different data type. And so, for instance, for this int1 and int2 column, we might want something smaller. For instance, a uint8. So that would be an unsigned integer with 8 bits. So that gives you value between 0 and 255. That may perhaps be enough for the data you want to represent. So again, we use this dictionary thing. And int1 is mapped to uint8, int2 is also mapped to uint8. Okay, you might say, okay, but what's this uint8 thing good for? Because numbers between 0 and 255. Well, for instance, color values. If you have RGB values, they will be numbers between 0 and 255. Okay, so let's load and let's do the info thing. You see that the data types are as expected. And you also see that the memory usage has dropped to 4 megabytes from 6.1. So basically, we are squeezing our data quite a bit. Okay. Then, actually, these guys here, binary 1 and binary 2, they just had very small data. So that was actually just categorical data. And also, cat1 and cat2 were just letters between A and C. So I can import those as category. Okay. Doing that and again showing the size. So now we're down to 1.3 megabyte. coming from 6.1, so that's a factor of 4, which we are gaining in memory. So that, of course, is quite a bit of a save in memory, and that will let you work much more comfortably on the one hand, and on the other hand, allow you to deal with larger data sets. There is also an additional advantage, for instance, for floating point numbers. Essentially, operating on float 32 can be twice as fast as operating on float 64. So that's an additional advantage, and the same with integers. So that is important as well. So then the question is, of course, how do you choose your data size? Well, that depends on what your data means. If you have measurement data, most likely float 32 will be enough, because I don't know many people who do measurements, actual measurements, with a precision of 15 significant digits. I don't think there's anyone here who knows people who do that. So typically, if you have 7 digits of precision, which you have with the float 32, that's probably good enough. With respect to integers, well, if I'm dealing with a color space, so RGB values or similar, a uint8 is perfectly fine, because those values are guaranteed to be restricted between 0 and 255. Of course, what you have to look at is the maximum number, positive and negative, which you can represent. And so basically for 8-bit, that would be signed minus 128 to 127. For 16 bits, because you also have int 16, that would be between minus 16,000 and 16,000 something, if memory serves. And then, or is that 32,000? I never use that, so I always have to think hard in order to get that right. Basically, it's minus 2 to the power 15 up to the power 15 minus 1. That's always correct, even if I don't know the exact number associated to that. And then, of course, int 32 would give you numbers between minus 2 billion and 2 billion. So, yeah, choose your data type according to the semantics of your data. That's the important thing. And if you have categorical data, it's a good idea to actually use that. Okay, what am I doing here? Yes, so basically the category thing. So basically this is just that I have a single category thing. As you can see, I have 100,000 values. I have a single column. The total data frame takes 100 kilobyte, give or take. So that basically means that although this is binary data, which in theory you could represent with a single bit, 8 bits are used in order to encode that. So 8 bits, 1 byte is the minimum addressable space in memory. So that's why this is 100K rather than, as you might expect, 100,000 divided by 8K. Anyway, and this would be the same. That's for the A to Z. So they can also be represented as categorical data. So this is approximately the same size. Okay. So this is the same for integer columns. Let's not go there. But you see that if we have a uint 8, that indeed it's similar in size. Okay. So let's look at some failures. What happens if you don't do the right thing? So basically, if you have a data type that is not appropriate for your data. So I create a data type manually. I use that using the data frame constructor, so basically the data frame function. The argument is a dictionary with the column names and then the values. And as you can see, the values of A are just very innocent looking integers. The values of B are also innocent looking integers, except that there is 283 and minus 1. And then for C, I have floating point values, where this one is larger than I can store in a float32, and that one is smaller than what I can store in an int float32. The other values are pretty innocent. Okay, so I create that data frame. Great. Okay, by default everything's fine because I've got int64 and float64, no problem. Okay, let's write that to a CSV file. Okay, so there is a function toCSV, which, you guessed it, creates a CSV file out of your data frame. Okay, now I can read it, and what I'm doing is I'm specifying as types uint8 for A and B and float32 for C. Okay, I'm not interested in an index column, so that will be 0. Okay, so as you can see, I get a warning, so that's already interesting. So an overflow has been detected in a cast. Okay, yeah, that's somewhat uninformative because it would have been nice if it would tell me in which column. It doesn't, but this already tells me that something is fishy. So let's have a look at info. This is as expected. So we get uint8, float32. That's all fine. But now if we look at the data frame, you see that we have some issues. So column A is normal, 3, 19, 5, 7. That's not a problem. But here is a problem. Because if memory serves, the second element was 283. No, sorry, I think that the third element, let me check because I don't remember which values I gave exactly. So if you look at the second column, then the third and the fourth are problematic, 283 and -1. But what we get is 27 and 255. So basically we had overflow. So the 283, 283, if we subtract 256, we actually get 27. So basically this is overflow. And similar for -1, -1 actually overflows to 255. So if we look at our data frame without knowing our data source, this looks okay. For column B at least. For column C, we get some values which are also somewhat unexpected. We get an infinite. That was for 2 to the power 50, 10 to the power 58. And then we get -0 for 10 to the power minus whatever it was, 103 or something. So there we get -0. So yeah, you have to be a little bit careful here what you do. Pick data types that are appropriate. If you don't, you get weird results. At least you get a warning that something is fishy, but it's up to you to determine what is going wrong and why it's going wrong. So setting your data types is very useful, but you have to be a little bit careful how you do that. Okay, any questions about this? All right. And then perhaps a bit on copy on write. So that's the last thing I'm going to talk about for pandas, and then I'll quickly show you the equivalent in dollars. Okay, so you might know that if you create a slice out of NumPy array, that you actually get a view, not a new array. And the situation is somewhat similar in pandas. So basically, let's have a look. We have a data frame, and again I construct one, in this case with 4 columns, and all those 4 columns are just random numbers. They are taken from a uniform distribution between -1000 and 1000, and there are again 100,000 columns. And then the first two columns are floating point, the next two columns are integer in 64. Okay. Then if I show you that data frame, the info for it, as you can see, I have the columns which I expect, 100,000 rows, nothing out of the ordinary. Okay, data describe. As you can see, you get what you would expect. So basically, the minimum value for column 1 and column 2 is very close to -1000. The maximum value is close to 1000, and similar for the integers, it's just -999 up to 999. So nothing unexpected. Okay. So now we select the 50,000 first rows out of that original data frame. So you remember the log object. I can also use an ilog, and that is just for integer location. So basically, that means that I can specify my index. It's integer, index location. So in this case, I want all the indices from 0 up to 49,999. Okay, so I use ilog, and I have data to. Okay, data to describe. No surprises. It's the same data. Of course, the count is different. The count is 50,000 rather than 100,000. But as you can see, we have similar ranges for the minimum and the maximum in column 1 and column 2. Okay, so what I now want to do is to, in data frame 2, in the original data frame, I want to clamp. Okay, so clamp means, or clip rather, clip or clamp. So basically, all the values larger than, in this case, -500 to 500, I'm going to replace by -500 and 500. And I want to do that in place, and I do that on data, column 1. Okay. And then you see that actually we get a very long warning. We have a future warning. So basically, that means that something is going to change about the behavior of this in the future. Okay, and the change is foreseen for pandas 3. So now we're at pandas 2.3. something. Pandas 3 will be out at some point in time. I don't know about the timing. But basically, when it happens, something in place method is never going to work. Okay. So let's see what happened. If we look at, and actually I better start with data. So let us first have a look at data describe. And as you can see, now for column 1, the minimum value is indeed -500. The maximum value is 500. No surprises. Here it is. So basically, if I do the same thing for data 2, then I get the same clip here. You see? So basically, my data in data frame 2 has been affected by what I do in data. So they are not independent, they share data. So although data 1 is not the same object as data 2, and of course I can immediately prove that. This will be false, indeed. They're different objects, but the underlying data is actually shared between them. So that means that if I modify data, that the corresponding data in data 2 is also going to be modified. So that is unexpected in the sense that's a bit spooky action at a distance. Now, that is not what the developers of Pandas actually want. What they want is that if you change something in a data frame, that change is restricted to that data frame and that data frame only. Okay, so what they have implemented is what they call copy on write. So as long as two data frames share a column which is not modified in any way, it remains shared. As soon as a change is made to a column, that column is actually copied. So that basically the change is local. You can already enforce that. So in Pandas 3, it will not be optional, it will be the case, but in Pandas 2, you can enforce that behavior by setting PD options mode copy on write to true. The default is false at this point in time. Okay, so we can do the exact same thing. We recreate our original data frame. We select the first 10,000 rows in 2. As you can see, everything's normal again. Okay, but now if I want to do that same operation on data, on the column 1, in this case on the column 2 apparently, don't know why I decided to do column 2 here, but basically in place is true. Now I do not get a warning. Now I get an error. So I can't do this anymore, which basically means that spooky action at distance is no longer supported. So basically, this is not the right way of doing that. So of course, data 2 has not been changed because nothing happened at all. So how should I do that? Basically, I can do that by using data clip. So directly applying clip to data, not to the column. Then I specify for each column the minimum version, the minimum value and the maximum value, and I set in place to true. So since I only want to, and let me change this because that's annoying. Let me make this column 1 as well, just to be consistent with all the rest. Okay, so basically I want to change column 1. So I set the minimum value of all the other columns, all the 3 other columns, to none. So that's basically what this rather odd-looking expression does. So let me break it down. The list with one element none is multiplied by 3. So that gives me a list with 3 elements, each of them none. Okay. The star operator is going to unpack that into a sequence of values. So this would have been the exact same thing as writing -500, comma none, comma none, comma none. And the same here. So it's just a little Python trick. It's not really relevant. Okay, so if I do that, no warning messages, no error messages. So basically, the second data frame has remained unchanged. So basically that means under the hood a copy was made of column 1 so that it did not get modified by this operation. And of course data has been modified, as you can see. It's clipped between -500 and 100. Okay, there is another way to do that. So what you can do is just say, okay, I'm going to take column 2 and I'm going to assign it to column 2 again. So also no problem, and same effect. Now on column 2, you see that it's clamped between -500 and 500 for data, and that of course data 2 is unaffected, as you would expect. Okay. So basically, this avoids surprises. So what I would suggest is that indeed, for future-proofing your code, that you indeed add this PD options, etc., mode copy on write to true, so that you don't have any issues with that in future. Okay, you can do some performance experiments. Basically, So if you do them, then essentially you notice that the difference between those two. So as you can see, if I do it column-wise, I get better speed up. I get better time than if I do that with a clip operation on all the things. So this is a bit faster, just to see how that affects the performance. Similar here. So basically, you gain a significant factor depending on what you're doing. Okay, that was it for, yeah, I want to save that because I made a significant change. Okay, any questions about this? Okay. Next, let's have a brief look at what polars look like. Okay, patient data. So this is the exact same problem, but now analyzed with polars rather than with pandas. So yeah, loading a CSV file or Excel file, same thing. Read Excel, easy. So no change here. We can describe just as we can with pandas. So basically, you get the same type of measures. Here you get a null count as extra, which you don't have with pandas describe. So it looks very similar with some changes. What you don't have, which annoys me a little bit, is this info function, and that's a bit annoying, but okay. So you also have the head function, you have the tail function, blah blah blah. Nothing very interesting here. You can get unique values just as you would with pandas. No changes. Here you have here things get interesting, because what we wanted to do here was the number of measurements for all 9 patients. So what we do here is we have our polars data frame. We group by patient. We want to maintain the order. That's just so that we get first patient 1, then patient 2, and so on. That's not really relevant. And then we do an aggregation. So we do an aggregation on the patient column. So pl.col creates a column object with the name patient, and then we do a count on that. And the alias is just the name of the column which we will actually have. And then you see that indeed we have 7 measurements per patient, except for patient 6. So as you can see, this is quite a bit of a different style. So you first group by, and then you apply the aggregate function. So this is a bit different in style. Okay. This is yet another query. So basically, we want all patients. We want specifically patient number 6. I can imagine that it's more similar to tidyverse. I'm not familiar with that, but I can imagine that it's taken more inspiration from. Well, it's essentially also taken inspiration from SQL, and I can imagine that tidyverse has looked very hard at SQL and thought it was a very good thing. So I can imagine that it's similar. Yeah. So we can filter. So in this case, I take the patients column, and I want only those which are equal to 1, and then I just want to select the date. So the select here comes sort of at the end, which is a little bit different than with pandas as well. And then you see that indeed you get all the times between 10 o'clock and 4 o'clock in the afternoon. And we can do the same thing for patient 6, etc., etc. Okay. So we also have a pivot function. Again, we have index date, and we do that on patient. And as you can see, of course, this is a bit or a lot, depending on your point of view, more annoying. And one of the things where Polars actually falls short a little bit, in my opinion, which is basically that you don't have multi-level columns. So this is more difficult to analyze. You do have the time series. The index indeed is again the date, but you have not this multi-level columns. So you have dose 1, that is dose for patient 1. You have temperature. Well, this is annoying. You have temperature 3, and that would be the temperature of patient 3, and so on. So this makes life, in my opinion, significantly more annoying. And then another thing which is unfortunate, as far as I understand, it's work in progress, but visualization is also not built into Polars. So you would have to create your own plot. It's not rocket science in this case. It's just I'm just using matplotlib, and I get a plot which is very similar to the one I got with pandas. But yeah, it's at the end of the day 4 lines of code rather than just 1. So yeah, okay. Also note that unless I start really fiddling, that the labels on the x-axis are in this case a little bit weird, but okay. So again, missing data, blah blah blah, the usual thing. I'm not going there. So very similar here. So we look at the date column, and then that's our selection, and we want to have any horizontal, so no axis stuff here. Here we have any vertical and any horizontal, no axis, where all are 0, and we alias that to as null. So basically we get booleans, and again we get true because there is a null for patient for here. This is the which is it? Yeah, for the for 1 o'clock, for 2 o'clock, and for 4 o'clock as before. So as you can see, and I should format this because this is too long, too ugly. Basically, this query is, yeah, it's a different style. So let me quickly reformat this a little bit to make it easier to read. Yeah, so this is a bit easier to read, but yeah. So it's maybe not that yeah, I probably didn't evaluate stuff, so yeah, this is not going to work. Anyway, so basically here I'm looking at a value at a time, and note that in this case, again, things are much more inconvenient. I really have to construct a date time object in order to filter my timestamp here. Remember, with pandas, I could just use the string representation of that date, and the right thing would happen. Here I have to use date time, I have to use strp time, blah, 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 blah. I have to specify the format of the time, as you can see. So, okay. It's all not as if it's showstoppers, but yeah. So you can also interpolate, basically interpolate function. Again, you specify a column object, etc., etc. So yeah, it's all a bit more verbose, but it's also more structured. So in that respect, it's worth having a look at. So this continues for the rest of the notebook, but I think you already got a flavor of what it looks like. Again, the big advantage of using pandas over Polars is that it's easier to get information about pandas. ChatGPT and friends are much more likely to hallucinate with respect to Polars. But yeah, it's worth it for the performance from time to time. So let me have a look at some timings. So basically, I create a data frame with 20 million rows, 3 columns, and I created a pandas data frame out of it and a polars data frame out of it. As you can see, the call is the exact same, so that's quite easy. If you look at the pandas data frame, you see that it uses 400 and almost 60 megabyte, which is something that you don't get immediately, but you can ask for estimated size of the pandas data frame, and then you see that it takes 480 megabytes. So the pandas data frame seems to be a little more compact than the polars data frame, but of course they're very comparable. Okay, so if you apply functions, pandas computing the mean value of column A takes 28 milliseconds. If you do the same thing with pandas, it is 7 milliseconds. Okay, 8 milliseconds. So yeah, something between 3.5 and 4 times faster. Now, these are numbers. These are very interesting numbers, but I really, in practice, when I'm doing interactive data analysis, I really don't care whether something takes 8 milliseconds or 30 milliseconds. I won't notice the difference. And this is a data frame with 20,000 rows. So you really need to get to very high numbers before this gets noticeable. Another example is column-wise mean values. So basically, I compute the mean value for each column over A, B, and C. As you can see, this takes quite long in pandas. It's 1.37 seconds. If I do that in polars, then you see it takes a bit more, a bit less than half a second. So yeah, this is something that you start noticing. But again, 1.5 seconds versus half a second in interactive work, do I care? I don't know. So creating new columns, again, polars is faster, but again, not by much. Dealing with categorical data, you see a very similar pattern, except that for once, actually, polars is a little bit slower. Okay, group by, also an operation that is quite useful. Polars wins out by a factor of almost 3. Pivots, where are my numbers? So again, polars is faster. Also, again, almost by a factor of 3. So indeed, polars is faster, but yeah, does it matter in practice? In the sense that if you are running this notebook on 20 million data sets, yes, it matters. Because on average, you would probably gain a factor of 3 by using polars rather than pandas. But for exploring a moderately sized data set, I'm probably not going to care. So that's kind of the bottom line here. Question? Yes, absolutely. So there are definitely alternatives to both pandas and polars, and one of the things which you will definitely want to do is to run certain things in parallel, and then Dask is also quite a good option. So there are many ways to do this with a higher performance. I will talk about Dask in an upcoming training, Python for HPC. So it's also an option to combine Numba with Pandas, which also can potentially speed up certain operations considerably. So there are quite a number of options to stick to Pandas, increase performance, or drop Pandas altogether and move to something different. NumPy is one option, depending on the type of analysis you're doing. You might even implement it at a lower level with another programming language entirely, or you could move to Dask in order to get things done in parallel. I mean, there are quite a number of options to deal with that. An advantage of Dask is that it has a very similar API to Pandas. So basically, rewriting that won't be that hard. Let's put it that way. Not everything you can do in Pandas is supported, but many things. Okay, so absolutely, you are perfectly right with that remark. I would definitely agree. Okay, any other questions about Polars versus Pandas? All right. Just because we're on the topic of alternatives, there is, of course, a fairly new kit on the block, and that's DuckDB. I rather like DuckDB, and as you can see, this material has been added really, really recently, so it's a bit rough. But again, I'm doing some of the analysis which I did with Pandas and with Polars on that same data set. So basically, what is DuckDB? DuckDB is a relational database in memory or on disk, depending on what you want. But basically, it's very similar to SQLite, which is part of the Python distribution, but it's way, way faster than SQLite. So I like it a lot. And it can be quite useful because also for data integration, because it can deal with much larger data sets. So that's already a good thing. It can work out of core, so your entire data set needs not be loaded in memory. So basically, it is in that respect quite interesting. But at the end of the day, what you're doing is executing SQL queries. So you need to be familiar with SQL. And frankly, as a data scientist, I don't think it's a bad idea to know about SQL. Yeah, that would be a good idea. Just to give you a bit of a flavor here, so this would be similar queries as we did for the data frame for the Pandas approach. So essentially, I'm selecting all the data for a patient. So patient, date, temperature, and dose from my data set. And in this case, I want to see only those rows where patient is equal to 6. So that would give me, just as before, 6 entries with 4 o'clock in the afternoon missing. Here is another type of query. So I'm going to select the patient. I want the number of temperatures as a high fever count. The maximum temperature I also want to see as max temperature. I'm selecting from my data set. And in this case, I only want to see those rows where temperature is larger than, okay, I'd have to change that to be consistent, 39. I want to group that by patient, and I want to order that by patient. And then you see that the results are different because originally I took 39.5. So here it was 39. Here it was, sorry, originally I took 39, here it's 39.5. So of course, results are slightly different, but you will recognize some numbers. For instance, patient 7 indeed had, I think, even 4 points where the temperature was larger than 39. So yeah, one of them was 39.3 if memory serves, so that would drop out here. Okay, so this is just to give you a bit of a flavor of how that worked. This is the maximum temperature versus the total dose. So it's quite easy to do this. So the pivot is similar to the one which you do in Polars, so also less convenient. And what you should remember is that this pivot operation is specific to DuckDB. It's not standard SQL. So that's something to keep in mind, that is not always useful. So you can read from other data sets as well, which I'm doing somewhere, I hope. This is the pivot thing, I think. Yeah, so here I read new data set. So I use a function which is of course also not standard SQL. I read this particular data set and I create a new table, patient metadata. And then you see that there's an additional table here, metadata, and so on. Okay, so just to give you a flavor, this can be used in conjunction, and that's the interesting bit. This can be used in conjunction with pandas because the result of the query can be transformed into a data frame. So to do certain computationally intensive pre-processing, it's useful to use DuckDB and then convert the end result into a pandas data frame for further analysis, for visualization, for further queries, and so on. So that is something to consider and an approach which is nowadays gaining a lot of traction. As I said, this is a bit rough. I have to refine this a little bit in order to structure it a bit more. Okay, so that's yet another alternative with its use cases and so on. Let me return to the presentation. So another thing which I want to mention is about pandas and Polars and DuckDB. So they can deal with quite a bit of data sources. So CSV we've seen, Excel we've seen, but for instance pandas and likely Polars, I would have to check, can deal with HDF5. Pandas can deal with SQL queries directly and can also immediately parse HTML. So that is quite convenient. DuckDB can, for instance, deal with Parquet files, with CSV files, and so on. Also with database queries and so on. So it's also quite powerful. Okay. I've totally removed those. Okay. So, with respect to visualization, another very important component of data science, there are a number of libraries which I consider quite useful for data science. I'm not talking about Matplotlib here because, okay, it's low level, it's useful, I use it all the time, but for data science, the more interesting alternatives. One of them is Seaborn. You already saw that in action with the LM plot, so the linear model plot. So for me, it's very interesting for data exploration. And especially if you're into statistics, then it's a really nice library. So it interfaces easily with both NumPy and Pandas, so that's convenient. And it's very nice to experiment with because it plays well with Jupyter Notebooks, as you would expect. And the selling point is that it's simple for rather complex plots. If you would like to do similar things in Matplotlib, you can. You can get almost anything done in Matplotlib, but it would take considerable effort. And it's Samuel Norman Seaborn. Okay, I added the thing here. Okay, so just to give you a little bit of an idea, let me go to the notebook. Seaborn. Okay, and that would be the one. Okay, so I have a data frame with some data. Don't remember what it is. Doesn't really matter too much. So basically, you can do a scatter plot quite easily. But this is just matplotlib, just for comparison. So this is just x-axis, y-axis, and data. Okay. I can do the same in Seaborn. So in this case, I would do a regression plot. So it looks quite similar, but we have reg plot here, and then you see that you get both the data points, but also the result of applying a linear regression on this data. I can actually also add some jitter to that data. So just in order, this is a different data set, y1 and y2. So basically, the points on the x-axis are discrete, and here I add some jitter in order to better see where the values lie. So that is something that is quite useful to do, because otherwise I would just get overlapping points, and then it's difficult to see where you have most points and so on. So that's why the jitter thing is useful. You can also very easily get estimators. So in this case, I want an estimator for the mean. So that would give me margins of error. So basically, that is also quite convenient. And then things get really interesting, because now I have a joint plot, and basically I get the same plot as before, which is here, but now I get the distribution of the x values and the distribution of the y values. So if you want to do this with matplotlib, good luck with it. You're busy for probably an hour trying to get this done. Okay, linear model plot I already showed you. So the new thing here is in fact that I can actually have columns based on a label in this case. So I want the column wrap in the sense that I want 2 rows and 3. Okay, size 3. Don't quite remember what the size does, honestly. But anyway, as you can see, there are 4 labels here: A, B, C, and D. And so basically, this is automatic. I don't have to specify anything, except that for the columns, I actually want labels. So very convenient. Size 3, I, for the life of me, don't remember what it does. We can have a look, but I don't think the documentation will be good enough to... Ah yeah, I didn't load anything, so I can't show you. But I don't think documentation is good enough to show it here. Okay. So yet another way to look at data. You can also play with the hue, so essentially with the color. And now in this case, I have an additional column which is either true or false, yes or no, and I get them separated. So this is very easy to distinguish between categorical data and still get my linear model plot. Okay. So here's a combination of a number of things. So I have and the hue and the columns. So as you can see, I can get rather interesting stuff just by specifying that. So it's each time, and that's the important point here, each time it is just a single function call, while with matplotlib I would have like 10 lines in order to get this done. At least 10 lines. Categorical data, so again, the illustration of jitter. So this would be a strip plot. Again, separated by hue. Box plots, separated by U. Violin plots separated by U, blah blah blah, bar plots, distributions of all kinds. So this is nice because you also get this hedgehog thing here, which also represents your discrete points. So that is additional useful information which you can switch on or off. So in this case, rug, so that hedgehog thing is actually switched to true, so that means that we get these vertical small bars here, which indicate the individual points in our data set. Okay, so in this case, I don't want the histogram, so I switch that off. That would be here the bar plot. So you can do anything you want. Bivariate data, so basically you get a distribution for one, distribution for the other, and essentially, as you can see, Pearson coefficient, blah blah blah, p-value, and so on. So basically, you get quite a lot of data with this, again, with a single command. Okay. So basically here in this case, I've got two graphs. So this is a facet grid based on binary, so I get no and I get yes, and then I can plot a histogram on x2. So basically this is the histogram for x2 each time, but separated by this binary criterion next to one another. So essentially, as you can see, you can do more sophisticated things, in this case based on label, and so on and so on and so on. So as you can see, the bottom line here is, this is a very useful library. You can make very nice plots or very informative plots with very little code. So in that respect, it is quite useful, and it can do very beautiful plots as well. Okay, so that's Simon, a big fan. HoloView is another interesting library. I'm not going to show you the notebook. I'm just going to use the slide because there is a story attached to it and it's easier to tell it on the slides. So basically, again, it's nice for exploratory data evaluation, and it's very easy to create overlays. So plots which are shown side by side, or plots which are superimposed on one another. It's good for parameter exploration. You have grid space and HoloMap, which I'll show you, and it interfaces well with NumPy and Pandas as usual. So basically, the things apply. So what I like about HoloViews is that it's really very simple to do rather complex things. So that's always a plus. Okay, there is a notebook. I'm just going to use, no, I'm not going to use the slides because I removed the slides. Okay, then I have to show you the notebook. Okay, HoloView, yes. Yeah, I think it's this one which I want to show you. Yeah, okay. So basically we import HoloViews as HV, nothing out of the ordinary here. Now, one of the things is I'm loading an extension, HoloView, HoloViews.ipython. So that makes sure that I can use it nicely in Jupyter Notebook. I read my data frame, whatever. So in this case, what is it? Essentially, this is real-world data. So this is a data set which was generated by a research group at my university, and they wanted an algorithm for certain things. It's years ago. If you're interested, you can look up the publication. I don't recall the exact thing. It's more than 10 years ago. But essentially, you have measurements of agents. So those were, if memory serves, pollutants in the air. And you also have the expression level of a number of genes. So these are the name of the genes. and those of you into bioinformatics will probably recognize those as householder genes. So yeah. And the ID column represents an identifier for a person who was part of this study. Okay, so we have a lot of these values. Okay, and basically just checking which genes we have, which agents we have, etc. So no surprises there. I can specify the output size. Okay, and I have an HV scatter of data, and now I'm comparing the expression level of IPO8 with YWHZ whatever. And then you see something that at least surprises me, in the sense that if I look at this data, I would say, okay, this is one group in my data, and that's another group in my data. Okay, so I had a look at the data which they provided me, and we discussed it. And I said, well, okay, it looks as if there are two distinct groups of patients in your data. And I said, no, that's not possible, because those are householder genes. There is no way that there is a difference in expression between all these. That should really be just a single linear relationship. There should not be two groups here. Okay. Now, I'm happy to believe that, except that I don't believe it, because if I look at it, if I believe my own eyes, there are two groups. Period. Okay. So essentially, you can look at this a little differently. So I decided to do some machine learning on this, just using a clustering algorithm, and that gave me two data sets. Okay, so basically, I had this group identified, and I had that group identified. Okay, so bringing it back to the data set, it turned out that it had to do with the data ID. So everything from 1 to 600 did something else than everything above 600. Okay, and it's very clear to see this. So yeah. Okay, so I did some linear regression on those, and as you can see, that's quite easy to do. So just using SciPy in this case, the regress function, and then putting that onto the plot quite easily. So we have the plot for curve 1, we have the plot for curve 2, and then we superimpose them, and now things get interesting, by just multiplying all those plots. So that makes sure that all the plots get plotted onto one set of axes. We superimpose them over one another. So batch plot 1 is the scatter plot, fit 1 is the line plot for the regression, and similar for batch 2 and fit 2. So combining plots is really trivial. It's just applying this multiplication operator, and that puts them on top of one another. Okay. So you can also plot the distribution then. So we have the fit functions, slope and intercept, blah, blah, blah. We get the data, and then we get a distribution plot. So that's another whole of use primitive, and you see that again we combine those two plots using the multiplication operator, and you see that red and blue are different. The average value is somewhere else, and also the width of the red curve is significantly higher than that. Okay, is higher than that of the blue curve. Okay, we can use a grid space. So basically, in this case, have the agents here on the y-axis. So this is agent 1, all of these 5 plots. This is agent 2, all of these 5 plots. And I then have the agent here. So basically, this allows you to see whether there is a trend here or not as a function of the presence of the agent, which there doesn't really seem to be maybe here, but you can get such plot very easily using HV grid space. You specify the plot and you specify the dimensions. And the plot is simply a dictionary between the keys, which are tuples of gene and agent, and the actual plot, which is just a simple scatter plot. Okay. You can also get that, yeah, that's not shown here. So basically, you can also do a holo map, and then you can simply select out of a drop-down menu the gene and the agent which you want to see. I would have to evaluate the whole thing. I'm not going to do that anymore. But basically, this allows you to quickly analyze data, and I really like the constructs. So what is missing here, if I would like to have these plots side by side, the only thing I need to do is to change that multiplication into an addition. Addition puts things side to side, so that is really, really trivial to do with holo views. Okay, maybe end of the story, because this was a real data science project. So I told them, well, okay, I don't believe you. I mean, there are two groups. I can identify them using clustering. It's pretty clear that it has something to do with the idea. So, I mean, tell me whatever you want. I'm not believing you anymore. And then they went back to their data and they realized something. They realized that the data was analyzed in two batches. Hence, in my notebook here, because this was done long after the fact, batch 1 and batch 2. And the blue batch was actually handled by someone who was much more experienced in wet lab work than the person who handled the red curve, the red points. So essentially, the data was unreliable. And you really, really see a significant difference between those two data sets. So essentially, the lab technician messed up in this particular case. But yeah, some data visualization and some persuasiveness sometimes can help you there. Okay, yet another alternative which I've also used quite a bit in practice is Altair. So it's mostly for interactive data visualization. So the result of an Altair plot is something that you can manipulate. So that's a nice thing. It's for interactive plots. So it's very nice for dashboards. It's JavaScript based, so that makes it easy to deploy it on a web server and have JavaScript happen in the background. It interfaces again well with NumPy and Pandas, blah blah blah, the usual. It's a bit different from plotting environments I'm used to. So it's based on grammar of graphics, which is basically declarative. So it's a different style of plotting, which makes it interesting, and there is a fairly steep learning curve for complex things. So I would say, unless you're willing to be really familiar with Altair, yeah, this one, of course, that's holo views, so that should be something else. But unless you really want to familiarize yourself with Altair, I would typically only use it in the context of dashboards. So basically, data analysis, which is kind of consolidated into a fixed workflow. Okay. I can give you a quick example, I think. Let's close this stuff. Let's have a look at Altair. Okay. So this I would have to execute, because otherwise nothing is going to happen. I create a data set, whatever, no one cares. I transform the data set. This is also a quite useful operation, this melt operation. this goes basically from a wide to a long format, because that's one of the annoying things about Altair. It can only deal with long type data. So basically, as you can see, my data frame has been transformed into something that has a value for x, a value for y, and also the function. So basically, I will have rows for sine of x, for cosine of x, and for tangent of x. And I have to encode it in this way if I want to use Altair. Okay, so basically, I create a selection object, which means that if I hover over a point, it will actually display x and y. Okay. I also have the selection, another selection object based on the legend. So basically, if I click on the legend, I will be able to activate or deactivate a function in the plot. Okay, then I have my actual plot. So essentially, this is for the points. I create a chart based on a data frame. Okay, then I say what type of plot is it going to be? Well, it's going to be a scatter plot, so mark points. I specify the size of my points. I say that they're filled, and I want this encoded as x and y. So x is quantitative, that's the Q, and y is quantitative. Okay, then I specify the color, basically by function, and that's n for nominal. So basically that is categorical data if you want. Then I specify the opacity, and that depends on the selection objects, in this case the legend selection object. Okay, and then we have the values. Between 1 is completely opaque, 0 to 2 is pretty transparent. Okay, and then as tooltips, I just have x, y, and a function. Okay, then additionally, I have a line plot. So I make lines with x and y, again quantitative. Color is again nominal function, and also the same opacity. And I add 2 layers to my plot, points and lines, and I add parameters. So basically my selection object and my legend selection, and I make the whole thing interactive. Okay, yeah, this is not for casual data exploration. So why do we bother? I hope it works. It seems to. Okay. So why do we bother? Because for dashboards, this is really nice. Why? I can, for instance, select this guy. So this is only my cosine or only my tangent, or both my cosine and my tangent, but not the sine plot, etc. So this is rather neat. Let me select all of them. What can I do? I can hover, and then you see indeed x and y, as well as the name of the function as well. So I can pen here, and I can, oops, what did I do? I probably clicked somewhere here, which I should not, which was not my intention. Okay. So I think if I click, I also get only that one. So if I manage to, yeah, okay. Now I don't know whether I can get the other ones. It's a bit more difficult because now, of course, they're grayed out, so that makes life a little more difficult. No, I can't. Okay, so yeah, let's just select. I can also zoom in or out just by using the scroll wheel, etc., etc. So this is a very interactive plot. I also have a menu here. As you can see, I can save this as PNG or SVG. I can view the source, etc., etc. If you wonder what Vega is, that's actually a JavaScript library. Under the hood, your specification, your Altair specification, is compiled into JavaScript, and that is essentially generating the plots in this notebook. Okay. So yeah, not for casual use, but rather useful as a library. I use this during the COVID period in order to create one or two web applications in order to support decision making with respect to opening and closing schools, these kind of things. Okay, so quite a number of references. So basically, this one is quite useful. This overview of data visualization types. So that gives you essentially quite a number of plots, and then a list of libraries which you can use to create those plots. So that can be nice. If you say, okay, I want a violent plot, then if you check that site, it will say, okay, you can do that with Seaborn, you can also do that with Plotly, etc., etc. Choosing color maps for heat maps, essentially. Color Brewer is really a good tool for that. And then for it's always a good idea to check whether your visualization makes sense for someone with color blindness. So you can have a look at that if that's of interest to you. Okay. Let me see. Okay. There are 4 things which we can talk about, and we don't have enough time to deal with all 4 of them. So I'll do a poll and see what interests you most. So we've got regular expressions, relational database access, web scraping, and graphic information systems. Okay. So let me try and do a poll. Yes. Okay. Let me stop sharing for a second because I get nauseous just by watching this. So, okay, so let's do multiple choice. Okay. The question is which subject? And the answer can be regular expressions. Alright. Nothing. Web scraping. And last but not least, geographical information. Okay, let's start the poll and let's have the votes. Okay, so let's stop the poll. Now you can see the results normally. So basically, it's clear that most people don't react. Regular expression is the most popular, and then web scraping, followed closely by object relational mapping. Okay, so it's clear that we're not going to talk about geospatial data today. Okay, so let's start with regular expressions and then certainly do web scraping. Okay, let me share my screen again. Okay. No, sorry, I need to figure out how this works, and it's a bit counterintuitive. Okay, yeah, that's better. Right. Let's share screen. Yes. No. Okay. Right. Good. So, regular expressions. There is a nice thing about regular expressions, and that is mostly that this is not about Python. So you can use regular expressions in Python, of course, otherwise we wouldn't be talking about it here. But the nice thing is if you know what a regular expression is and how to use it, you can do that in any programming language, because most programming languages actually either do support regular expressions out of the box, or there are very decent libraries in order to use them. So for instance, Java has its own regular expression library, Python has it, C++ has it in its standard template library, and so on. So almost all programming languages have regular expressions, typically even in their standard library. Okay, so question is, what is a regular expression? Essentially, a regular expression is a description of a language. Okay, what's a language? A language is actually just a set of strings. So this is quite abstract, but that's from a theoretical computer science point of view, what it actually is. So if a language is just a set of strings, then of course a language can be finite or infinite. So it can have finitely many words, or it can have infinitely many words. Okay, so of course the set of all strings is an infinite set. It's a countable set, but it's infinite. Okay, so there is a hierarchy of languages. At the bottom, in a way, you have regular languages, and they are included into context-free languages. Those are included into context-sensitive languages, and finally, we have the recursively enumerable languages, which is the largest set of all. So as you can see, regular languages describe sets of strings, but are not as powerful. There are less regular languages than there are context-free languages. Of course, less is a very loose term here, because of course the set of regular languages is infinite. The set of context-free languages is also infinite. So yeah, what does less mean? It's not really clear. But at any rate, there are context-free languages that are not regular languages. So how should you view this? Well, you are familiar with languages. I mean, English is a language, Dutch is a language, whatever your native language, it's a language. And at the end of the day, yeah, that is just a set of strings. The strings of all the sentences you can form in that language, and that are syntactically correct. And that's essentially your language. So what type of language would that be? Well, typically a language like English is a context-sensitive language. So basically it's not the simplest thing, but it's also not really the most general thing. So we are going to restrict ourselves to languages that are simpler, that follow certain patterns or that can be described using regular expressions. Okay, now, if you look at this mathematically, then we have this Chomsky hierarchy, which is mathematically very well defined. But if you look at Python regular expressions, they can express, in fact, more than just regular languages. They can express some context-free languages. Not all of them, but some. So that's something to keep in mind, that regular expressions is used loosely in the context of Python, and also in the context of JavaScript, because if I remember correctly, Java and Python have very similar regular expression grammars, so they can do very similar things. Okay, so a few examples of things that are not regular languages: HTML or XML. Those are not regular languages. Those are context-free languages. So using regular expressions to parse context-free languages is a bad idea. You will shoot yourself in the foot after a while, that's for sure. Okay. So can you write a regular expression that would describe all regular expressions? No, you cannot, because the language of regular expressions is in fact context-free. So yeah, this is all pretty abstract and mathematical, but basically, yeah, it gives you some restrictions on what you can do usefully with regular expressions and what you cannot do. So let's consider a few examples, and let's consider DNA. DNA is typically represented as a sequence of nucleotides, ACGT. Okay, so how can I describe all the strings that represent DNA? And let's forget about biology here, because there are most likely many sequences that wouldn't make any sense biologically, but let's just assume that any sequence of ACGT is going to be a reasonable fragment of DNA. Okay, so how can I express that as a regular expression? Well, I can say I have the set of characters ACGT. So the round brackets are the set, the ACGT are the elements. So any character must be either an A, a C, a G, or a T, and I can have multiple of those. The plus means one or more. So basically, that gives me a language. The shortest elements will be the string A, the string C, the string G, the string T, because those are length 1, and my regular expression says plus, so I need at least 1 out of ACGT. Okay. Then, of course, we start repeating. For instance, I could have 2 A's. I could have AG. I could have TC, etc., etc. And I can have something very complicated, like CAA, TT, CAA, etc., etc. So this is a set that is clearly infinite, because my DNA strings can be as long as I want. If I just consider A as a character, I have the string A, I have AA, I have AAA, I have a million A's, I have a trillion A's. So clearly, this is an infinite language. However, it's represented by just 7 characters. The 2 square brackets to denote my set, the 4 characters in my string, and the plus repetition operator. Okay. So let's say we have any DNA string that contains the string AAT. Okay. How can we represent that language? Well, there are a number of ways in which AAT can occur in such a string. It might occur at the start of the string. My string might just start with AAT. That would definitely be part of that language, part of that set of strings. It could be that it occurs at the end. And equally, it can occur in the middle. So, how can I represent that? Well, what I can say is that I must have AAT somewhere. That's in bold here. Those are these 3 characters. They will occur in my string, but they may be preceded by any combination of ACGT, 0 or as many times as I like. So notice, rather than a plus operator, we have a star operator. This star operator is again a multiplicity operator, and it says 0 or more times. So plus 1 or more time, star 0 or more time. Okay, so that means that if I choose 0 as a repetition, then AAT occurs at the start of my string. Okay, and similar for the suffix. The AAT might occur at the end of the string, hence again it can be followed by any ACGT 0 or more times. Okay, so implicitly, I have an additional operator here, which is the concatenation operator. So if I just have an expression followed by another expression, that means concatenation. So for instance here, A is followed by A is followed by T. The whole thing is preceded by any number of ACGTs. The whole thing is can be succeeded by any ACGTs 0 or more. So that's implicit concatenation, if you want. And then the star operator I've already explained. The shortest string in this language is going to be AAT. So not preceded or followed by anything. Then I might have an A at the start of my string and then AAT. Or a C at the start of my string, AAT. Or AACTE, no, not E, G, AAT, etc. So basically, as long as I got somewhere my AAT, I'm happy. So that's a second example of a language, and of course, again, it is clearly an infinite language. Okay, suppose that it should contain AAT or TAT, then I can use an additional operator, which is the choice operator. So the OR operator, if you want. And I can use brackets in order to group things. So the strings for this language must contain either AAT or TAT. And as before, that can be preceded by any combination of ACGT and can be followed by any combination of ACGT. So basically, the pipe operator denotes a choice. Okay. Yet another example: DNA that contains either AA or AACC. Okay. So of course I could do it exactly the way as before. I could say, okay, any ACGT and then AA or AACC. But I want to do it a little bit differently. So I will have AA in any case, because we have AA here, we also have AA in the second choice. So I can write this down as AA followed by CC optionally. So this question mark means it's also a repetition operator, 0 or 1. So either we have AA and then the question mark is not occurring, or I have AACC, where CC then does occur. And then again preceded and followed by any number of AACCs. So the question mark operator is another repetition operator, 0 or 1. Okay, so that's basically our grammar. Let's take another example. So Belgian phone numbers, you might know that we have, okay, forget about mobile phone numbers for a second, but if you look at landlines, you might know that we have two types of numbers. We have area codes, and an area code can either be 2 digits, the first of one is 0, or it can be 3 digits, and the first of that is again 0. Okay, and then basically if I have a 3-digit area code, I've got 6 digits for the actual phone number. If I have a 2-digit area code, I have 7 digits for the phone number. Okay, so in total, you always have 9 digits. Each Belgian landline number has 9 digits. Okay, how can I write this as a regular expression? Well, it should start with a 0. That's clear. And then there are two options. Either I have a 2-digit area code or a 3-digit area code. Okay, at any rate, the second digit has to be non-zero. That's for sure. Because I don't have something like 00, because that would mean that I want to make an international call. So there's only a single 0, and that's at the front. So that means that the second digit must be 1 up to 9. Okay. And then optionally, it's followed by any digit, 0 up to 9. It's optional because there is this question mark. Okay, so this 1-9 is between square brackets. So again, that's a set of the digits 1, 2, 3, 4, 5, 6, etc., etc. So basically, if you have a character dash another character, that means that character, all the characters in between up to the character you specify included. Okay, so that's a shortcut for square bracket 1, 2, 3, 4, etc., etc., 9, close square bracket. So this is a shortcut. And then again, \d is another shortcut. It just means any digit. There is a caveat here, but okay. All right. Then the first digit of a phone number, so forget about the area code, we dealt with that. The first digit of an area code, of a phone number is always non-zero. So again, we have 1 to 9. And then, of course, it's followed by 5 or 6 digits. Okay. So this curly bracket here thing, that's another repetition operator. So that says minimum m, maximum n repetitions. So that means any digit, 0 to 9, 5 times or 6 times, nothing else. The slash here is just a literal slash which separates the area code here from the phone number here. Okay. So that's yet another operator. So another question is this really describing all the Belgian phone numbers and only the Belgian phone numbers? Landline numbers, forget about mobile, forget about special numbers, 0800 and that kind of thing. So basically the regular landline numbers. Is this a good regular expression? So for instance, area code of Leuven is 016. So yes, it starts with a 0, that would be fine. Then we have a 1, that's fine. Then we have any digit, that would be the 6, and that's fine. Slash, and then for instance, 260932. So yeah, the 2 of the 26 would match, would be matched by this part. And then we have 5 digits, 6, whatever I said. So basically, yes, that would match. So that seems okay. Let's say we have a phone number with in Brussels, so that would start with area code 02. So yes, it's a 0, that's fine. 2 is in the set 1 to 9, that's fine. Then there is a slash. So okay, that's okay because the third digit is optional thanks to the question mark operator, so no problem. And then it would be followed by, say, 4 and then 6 digits. So the 4 would fall into this category, and I would have 6 digits here. So that's also fine. So it seems as if indeed it covers the landline numbers in Belgium. So in that direction, it's actually fine. Okay. So now the question is this a good regular expression? Well, maybe not. Because, for instance, 025 slash followed by 3 and 6 digits would also be okay. So that would give me 10 digits for my phone number, and that is not a valid landline number. Conversely, I could also have a valid a member of this set like 02 followed by a digit and 5 digits. So that would have only 8 digits, which again is not a valid landline number. So all phone numbers are covered, but my set is too large. So that's something that you always have to keep in mind when you are using regular expressions. Do they really cover everything you want to cover? And additionally, do they cover things which are actually not part of your set? So that's quite important. There are other things like, for instance, all the strings. So basically that would be the dot is any character, almost. And the star means 0 or more. So that gives you the set of all strings, including the empty string. Okay, so this would, for instance, be a regular expression that could denote an email address. So we've got the @ sign, then we have the domain name, and we have the address. So \w means any character from A to Z, including numbers and an underscore, capital, lowercase, uppercase, lowercase, one or more. And then optionally, we have a literal dot. So \dot means a literal dot. And then any characters again, one or more. And that's optional. So basically that would mean that my email address could be capital H at something something. So the domain name again is then another string, and then optionally a dot followed by more domain names. So again, this is a regular expression that is in fact a bit too wide. So don't verify regular expressions. Don't verify email addresses with a regular expression that you formulate yourself, because the opportunity plus addressing. I don't know what plus addressing is even, and that points to the root of the issue. If you look at the specification for what a valid email address is, it's 90 pages long. So it's really non-trivial. The chance that you get it right is absolutely 0. So there are special libraries in order to verify email addresses. So I include this explicitly to say don't ever do this, because this is going to kill you. And I have no clue what plus addresses are. So I don't know these 90 these 90 pages of the specification. So basically, don't do that. So this guy here, round brackets with the question mark column, that's grouping things. Okay. So this is actually equivalent to brackets in mathematics, if you want. All right. So don't do this in practice, bad idea. Okay, so characters, there are some characters that need to be escaped. So the top, obviously, that's \t, new line, \n, carriage return, \r, a backslash, just \\, and also all the brackets, because they all have special meaning in regular expressions. So if you want that character, you have to escape it with a backslash. And also all the things which serve as operators. So the plus, the dash, the question mark. Ah, yeah. Okay. Okay. I didn't even know that that was legal. So those you also have to specify. Oh, yeah. Okay. I have to look into that because that might be interesting. And also the dot is special. So that's important. Remember, the dot has special meaning. If it's not escaped, it means any character, almost. All other characters are literal. So then character classes, if you simply specify a character, then that's the set of that character, a singleton of that character if you want. So a literal enumeration of characters gives you the set x, y, z. This is a range, so that would also be x, y, z. expressed mathematically here. You can also negate that. So basically this would be the set complement if you want. So basically that would be any character, but never an X, a Y, or a Z. Backslash W, we already mentioned that. Then backslash W capital, that's again the complement of backslash W. Backslash D, all digits. Backslash capital D, anything that's not a digit. Lowercase s, any white space, that can be a space, a tab, a form feed, carriage return, a new line, and a vertical tab. So all of this is valid white space. And then, of course, capital S, anything but white space. The dot, anything. Yeah, not quite. And backslash n, so a new line, is not mapped by dot. So that's the only exception. Apart from that, anything is in dot. Okay, now that's all very nice, but all of this, what I'm doing here is ASCII. So if you are in a Unicode world, and with Python you are in a Unicode world, then essentially if you have UTF-8, things might be matched, for instance for a digit, that you don't expect to be matched. For instance, the character for 1/3 or 1/2 will, if memory serves, be matched by backslash D. So yeah, be very careful when you start really dealing with Unicode, because that makes this an order of magnitude more complicated. Okay, so operators concatenation is implicit. We already mentioned that. Choice is the vertical bar, so the pipe. And then repetition, we have quite a number of them. You can say, okay, I want exactly n repetitions. Or I want at least n, at most n. Or I want as many as you like, 0 up to n, or starting from n up to as many as you like. And then you have the classic tree, which is 0 or 1 question mark, star 0 or more, plus 1 or more. Okay, and we have longest match semantics. I'm not going into the details, that's on the next slide. So we have greedy versus non-greedy operators. By default is greedy. So also to show you that parsing XML-like languages or HTML-like languages is dangerous. So basically what I want is I want to match a substring here. So the question is, what would this match? So we start with a literal less than, okay. Then any character, at least 1 or more. And at the end of the day, I should have a closing, larger than. So now there are two options. Either this regular expression matches from the beginning of the string up to the first larger than, or to the last larger than. And it's longest match semantics, so it's going to be the second case. So this is going to be matched, which may or may not be what you want. Okay, if it's not what you want, you can actually use a non-greedy operator. So basically, then you would do plus question mark. So that will do a shortest match. So basically, it will stop matching as soon as it can match the next character. So this question mark means take the operator, but use non-greedy semantics. And you can apply that to any repetition operator. So that can be applied to plus, to star, to question mark itself, but also to the curly brackets forms with minimum and maximum values. You could also do this differently. You could say, okay, I want to match less than, and then any character that is not larger than 1 or more, and then this one. So this would match the exact same thing here. That would match this. But again, This is HTML or XML, depending on your point of view. So essentially, don't do this because those are, in fact, not regular languages. So you should use different tools for that. Okay, and this is an example of that. Let's not go there. Okay. Right. So this would be to denote a string with digits only. So the caret here means the start of the string. The dollar means the end of the string. So those are not characters that are matched. They are position indicators. And we have several of those. Besides caret and dollar, you also have things like \b. That's a word boundary. So then you also have capital B. That is not a word boundary. So basically an empty string in Word. So that's to set boundaries, which can be very convenient to make your life quite a lot easier. So those are essentially anchors. So they match the empty string. So you can have a start of the string marker, \a, similar to caret, the end, \z, similar to dollar, and this is to do with new line. So typically you will use those. So before or after alphanumerical sequence and within an alphanumerical sequence. So those are your anchors. Okay, so what can we do with it? Well, we can check whether a certain string matches our regular expression. And we can do that using the RE module in Python and the match function. So basically, first argument is the regular expression, second argument is the string we want to mention. Okay, so if this matches, then it will return something that is not none. If it doesn't match, it will return none. So hence there is none expression here. So basically, this expression would match this string. So we get true. And this expression would not match this string. So we get false. Okay. The R string is very useful in the context of regular expressions. So an R string is a roll string, and that basically means that backslash doesn't have a special meaning. And that makes your life with respect to regular expressions much more convenient, since of course there are a lot of backslashes in regular expressions. If you would always have to escape the backslash, you would be extremely unhappy. So that is quite useful. So basically, match starts to search from the beginning of the string. Search looks somewhere in the string. It need not be, the pattern need not occur at the start of the string. So if we would do RE search for this regular expression on this string, it would actually match. So remember the difference between match and search. Okay. So always use roll strings for regular expressions. It makes your life a lot easier. So this is an example. These are three strings. We have hello \n plus world. We have hello \n plus world, and we have the roll string hello \n plus world. Okay, so basically this would be the result of the first one. So the \n is a literal new line here. Then for the second one, you see that we get hello \n. So the backslash here is a literal backslash. And for the R string, we automatically get the \n here. So basically, these two are equivalent, but I would argue that the second one, so basically the roll string, is much more easy to read and less error prone. Okay, You can add options to ignore the case. So you could write a regular expression like this, but actually what you can do is when you have the match function, you can add as an optional argument re ignore case or just re.I. Okay, I'm going to skip this because I want something else. Let's not go here. So another thing that you can do with regular expressions is extracting data. So if I'm only interested in part of a string, I can take that out using a regular expression. So for instance here, I have a regular expression. It matches begin or end, and then a space, and then any sequence of characters, alphanumerical characters. Okay, and I've enclosed them in round brackets. So basically, I'm able to extract those. So if I apply that to begin data, then begin is matched, space is matched, and then we have any sequence of alphanumerical characters, so data is going to be matched here. So now I have a match object, n, so the result of the match function, and I can use group 1 and group 2. So group 1 would be whatever is matched by the first pair of braces, first pair of brackets. So that would be, in this case, begin. And group 2 would be anything that's matched by the second pair of round brackets, and that would be data in this case. So this is very nice. I can use a regular expression to take strings apart. Okay. You might wonder, okay, why is there group 1, group 2? Normally we start counting at 0 in Python. Yeah, that's true. And so group 0 also exists, but that's the entire string that has been matched. Okay, so this works for RE search, for RE match. That's all the same. Okay, so don't confuse grouping and capturing. Grouping is round bracket, question mark, colon. This is capturing. So capturing groups, but it's more work. So if you don't want to capture, then it's better to use just grouping braces. If you want to capture, life is easier. Okay. You can name groups. Let's not go there. Just look at it because the syntax is rather awful. I always have to check when I've not used regular expressions for a while how I should write this. This is more robust, so it's definitely good practice, but it's making your regular expression looking a bit more cumbersome. Okay, I'm also going to skip this because the last thing I want to show for regular expressions is, in fact, substitution. So I can also substitute things. For instance, suppose that I've got something horrible went wrong here with the formatting. So basically, I've got this string, and I want to replace it so that each part here is enclosed by quotes. Then what I can do is I can match for sequence of characters that are not comma, and I use capturing brackets, that's the round brackets in red, and I want to replace them by what I captured, so that's \1 and quotes. So basically I would get this. So this is my original string. I do an RE sub, and I'm going to match all the parts of my string, replacing it by single quote, whatever I matched, single quote. And I do that on my string, and then basically what I get is indeed every element of my sequence quoted by single strings. So these are the three things you can do with regular expression. On the one hand, matching, so checking whether a string has a form you want it to have. Extraction, taking a string and getting parts out of it according to certain patterns. And substitution, so you have your original string and you substitute values in sophisticated ways. That's essentially the idea. Okay, this was very quick because I want to show you something about screen scraping. So basically, web scraping, one of the things is it's very brittle. I've done quite a number of applications back in the days that relied on web scraping. If I can avoid it, I will avoid it. Because style changes, a minor change in, for instance, the style, the CSS or whatever, is going to completely kill your script. So doing this in a robust way is really cumbersome and really hard to do. So that's an important caveat. So that means that if you have a choice between scraping an HTML page and using, for instance, a REST API to get the data, use the REST API, because this is hard to get right. Okay. Anyway, sometimes you really don't have an alternative. Okay. There are many frameworks for that. There's even stuff to do this in the Python standard library, but I like Beautiful Soup. So basically, if you just need tables, then just use pandas. It can also do that. But okay, Beautiful Soup. You use a web page using your lib. That's part of the standard template or the standard Python library. So basically, your lib request, and that gives you essentially your page. Okay. Yeah, Python 2. This we can leave out. Okay. Then basically, what you do is you take that page. You specify which HTML library you want to use, so in this case HTML5lib, and you get a soup object which you can use in order to extract data. Okay, so basically you can then, for instance, get the string representation of the title. So title would be an element of your page, and you want its contents, so basically the string. So that's how it works. It's really easy. Of course, there is the implicit assumption that the page does have a title element, but you don't need to worry where it is. You just get it. Okay. So essentially, if I want to get the first element with a tag, so that would be an A element in HTML, I can just do soup.a. And that will give me the first anchor, wherever that anchor is in the hierarchy of my elements. So that's quite convenient. If you want them all, so basically if you want all anchors, okay, no problem, soup find all A. And that would give you all the A elements. Okay. If you want the element content of A, and then basically that's just string. So that's the textual content of an element. If you want an attribute, for instance, for an anchor that could be an href, then you just specify a.get href. So as you can see, this is quite simple to quickly get something together to scrape stuff from web pages. Okay, I would say let's conclude here because I'm 20 minutes over time already. So let's conclude here. Are there any additional questions? Okay. Yes, there is indeed quite a lot of stuff to delve into. So even about pandas, which we treated rather extensively, there is still quite a lot of additional material. But you have access to that, so feel free to explore. Feel free to fork the repository. I'll put the link again in the chat for those of you who missed that at the beginning. And I'll stop sharing. Okay. Also, as I mentioned, the recordings will be available by this evening or tomorrow morning, depending on the time. Okay, so thanks for attending. I hope it was useful, and perhaps see you in another training.